Hi everyone, welcome to PrepFusion. So in this video we are going to study about Fermi direct distribution. So what is this Fermi direct distribution that we are going to see, and this is going to be our final video for basic semiconductor physics. So what is this Fermi direct distribution? So let's just say this is your semiconductor. In this semiconductor you will be having some energy states. Energy state could be there in conduction band, it could be there in valence band. Okay. So let's just say this is my energy state E. Now on this energy state either electron will be there or it will not be there. Either there will be electron or it will not be there, right? So Fermi direct distribution comments on finding the probability of electron on a particular energy state. So probability of finding an electron on a particular energy state, that is given by Fermi direct distribution. Since it was given by Fermi, so I will write down F. Probability of finding the electron at a particular energy state E, that is given by 1 upon 1 plus e to the power E minus EF by KT. K, you know what is K? What is one constant? T is the temperature in Kelvin. 1 upon 1 plus everything you know. E is the energy level. E is the energy state, not energy level. E is the energy state. The energy state where you are finding the probability of electron. And EF is the Fermi energy level. Now sir, what is this Fermi energy level? So it is just like a reference energy level. It is practically not existing. What I mean to say is that in your semiconductor there will be conduction band, there will be valence band, that's it. But we will define some reference energy level that is known as Fermi energy level. So this is your Fermi energy level. It could be somewhere between conduction band to valence band. Is that okay for you? Even this can go into the conduction band as well, it can go into the valence band as well. We will discuss all these things, but as of now what you need to consider that EF is nothing but a reference energy level which is practically not existing. We are just defining it. Why we are defining it, you will understand. So have some patience. So as of now what we have studied, Fermi direct distribution comments on the probability of finding an electron on a particular energy state, not energy level. Okay, comments on the probability of finding an electron on a particular energy state, and that probability is given by 1 upon 1 plus e to the power E minus EF by KT. E is that particular energy state, EF is Fermi energy level, KT you already know, right? So this is what has been written. It tells us about the probability of finding an electron in a particular energy state. So just notice this word, energy state, not level. A very important point, very important point, that it comments on the probability of finding an electron at energy state, not energy level. Okay, and at a certain temperature as well, because temperature can the temperature can also vary, right? What is E? E is equals to that energy of the state. EF is the Fermi energy level. What is Fermi energy level? We will discuss about that. K is the Boltzmann constant and T is the temperature. Now what I am saying, the temperature is 0. Temperature is 0 Kelvin. And E is greater than EF. What I am saying is that you need to find the probability of finding the electron at energy state E, which is above EF. What I mean to say is that if this is your EF, then energy state E is here. So E is above EF and temperature is 0 Kelvin. So what will happen? 1 upon 1 plus some positive value e to the power E minus EF will be positive because E is greater than EF. So some positive value divided by 0 Kelvin. What that will be equivalent to? 1 upon 1 plus something divided by 0, or that would be infinity. And what is the value of e to the power infinity? Infinity only. So what is the answer you are getting? 0. So probability of finding an electron at an energy state which is above the Fermi energy level at 0 Kelvin will be equals to 0. What I am saying, let me repeat it. Probability of finding an electron at the energy state E, which is above Fermi energy level at 0 Kelvin, will be equals to 0. That means if you are at 0 Kelvin and your energy state is above EF, then you will not find any electron here. Is that clear to you or not? Okay. Now let's see the second thing. Now my energy state is below EF. Now my energy state is below EF. This is my energy state. Okay. Now I need to find the probability of finding an electron at this particular energy state. That would be given by you should write down this formula at least 5 times in your rough notebook. Just now write it down, this formula, at least 5 times, because it is very, very important. This whole lecture will be going towards this particular formula, and surely the question is coming from this particular formula. 100% I am saying question is coming. So at least write down 5 times. 5 times you write down this formula. 1 upon 1 plus e to the power e minus ef by kt. Okay, yeah, so let's do it. 1 upon 1 plus e to the power e minus ef is negative now, right? E is less than ef, that means e minus ef would be negative, divided by 0. So what you will be getting? 1 upon 1 plus negative divided by 0 e to the power minus infinity, right? Negative divided by 0. Let's just say minus 1 divided by 0. So that would be minus infinity. Minus 2 divided by 0. That would be equals to minus infinity, right? And what is the value of e to the power minus infinity? That is 0. E to the power minus infinity is 0. So what is the answer you are getting? 1. So here you are getting answer 0 and here you are getting answer 1. So what you will say? At 0 Kelvin temperature, probability of finding an electron below Fermi energy level is 1, and probability of finding an electron above Fermi level is 0. That means at 0 Kelvin, all the electrons will be lying under the Fermi energy level. Again, let me repeat the statement. At 0 Kelvin, all the electrons will be lying under the Fermi energy level. Do you understand by this? Do you understand this line or not? E is less than EF means energy level is under Fermi energy level, and E is greater than EF, that means your energy state is above Fermi energy level. If I am saying energy, here I should use the word energy state, but in the language when I am speaking, sometimes if I call level, then also you should understand that I am calling state only. E is the energy state, but for EF we use the word Fermi energy level, okay, but E is the energy state. So in language, sometimes if I mess up and I say E is the energy level, then you should say that E is meaning for energy state only. Are you able to understand what I am saying? Because in the language, because we will keep on saying Fermi energy level, so here I can say E is the energy level, but it is actually energy state, okay. So E is the energy state. Do you understand the meaning between energy level and the energy state? Yes, you already understand, because in the basics we have seen. What is energy level? Energy level is like a floor and energy state is like a room. So on one floor there could be multiple rooms. So on one energy level there could be multiple energy state, right? So that you have already understood. So probability of finding an electron below the Fermi energy level is 0, and probability of finding an electron below the Fermi energy level is 1 at 0 Kelvin, and probability of finding an electron above the Fermi energy level at 0 Kelvin will be 0. All good, all fine. So let's draw the Fermi energy level for intrinsic, N type and P type. So this is what is written: at 0 Kelvin all states below EF are full and above EF are empty. So what do you think? At 0 Kelvin, what is the scenario in intrinsic semiconductor? All the electrons will be lying in the valence band, and there will be no electron in the conduction band. So where I can draw the Fermi energy level? Sir, even if you draw here or here or here or here, sir, everything would be fine. Right? Because what is the condition? That, sir, below Fermi energy level everything should be filled, and above Fermi energy level everything should be empty. So sir, if I draw here, then you would say that below it fine, above it there is nothing, yeah, it is also fine. But actually we draw it right in between, okay, right in between, because there should be a symmetry, no? Like below this everything is filled, above this everything is empty. So this is your Fermi energy level of intrinsic semiconductor, EFI. What about N-type semiconductor? Where I should draw it? In N-type semiconductor, what will happen? You will dope some donor atom, and since you have doped the donor atom, each donor atom will be giving you one electron. This electron is nearly free. This is not completely free. Since this is nearly free, so it will make an energy level just below the conduction band, because it requires very less energy to get into the conduction band. But at 0 Kelvin, it is not getting energy. That means at 0 Kelvin, it will be there in the donor energy level only. It is not getting into the conduction band. So at 0 Kelvin, this will be the scenario. There are some electrons in the valence band. There are these are the bound electrons. These are nearly free electrons, not completely free, nearly free electrons, which are ready to go into the conduction band just as they get some energy, but they are not getting the energy. That's why they are here. So what do you think where I should make my Fermi energy level? So this is where I will make my Fermi energy level. So this is your Fermi energy level for n-type semiconductor. And what do you think here? This will be interesting. Where I should make my Fermi energy level? Here? No. It is about the electrons, no? It comments on finding the electron. It comments on the probability of finding the electron. Do you really think that acceptor atom is having any electron? No, acceptor atoms are having the holes, right? Because if you dope acceptor atom, they will give you a hole which is ready to take electron. So this is the vacancy for the electrons. So where I will make it? Here I will make it. Someone will say that, sir, even if you make it here, then also definition is satisfied. Definition says that below Fermi energy level, everything should be filled. And above Fermi energy level, everything should be empty. So still this condition is satisfied. But if you are making this above the donor energy level, so this you will make below the acceptor level, right? So now also the condition is satisfied, no? That above everything is empty. These are empty only. And this is also empty only. And below this everything is filled. Yes, below this is everything is filled. So this is your Fermi energy level of p-type. So in n-type, Fermi energy level is near to the conduction band. In p-type, Fermi energy level is near to the valence band, right? Say yes or no. And in intrinsic, it is right in between. In the intrinsic semiconductor, the Fermi energy level is right in between. Is that clear to you or not? Okay. So I am asking you this question. Find the probability of finding electron at energy state which is 0.1 electron volt above the Fermi energy level. Consider room's temperature. So what will be your answer? Sir, they are asking above the Fermi energy level. Above the Fermi energy level. So probability of finding an electron above the Fermi energy level, we know that everything will be filled below the Fermi energy level. Above the Fermi energy level, everything will be empty. So sir, this is the answer which is wrong. Because everything that we discussed till now, that was for 0 Kelvin. What is the temperature given here? 300 Kelvin. So what you need to find? You need to find the probability you need to find the probability of finding an electron at an energy state which is 0.1 electron volt above the Fermi energy level. So if this is your so if this is your Fermi energy level, then this will be your energy state. What they are saying? The difference between E and EF is 0.1 electron volt. So E minus EF is given as 0.1 electron volt. And what will be the value of KT at room's temperature? 0.0259 electron volt at T equals to 300 Kelvin. This thing also we know. So what we need to find? Probability of finding an electron at this energy level E, that would be equals to 1 upon 1 plus e to the power E minus EF by KT. So 1 upon 1 plus e to the power 0.1 divided by 0.0259. So when you solve it, you will get the answer 0.02. So this is the answer. Okay. So not 0. Blindly you are not going to put 0. Whatever that we discussed, that below the Fermi energy level, everything will be filled. Above the Fermi energy level, everything will be empty. That was at 0 Kelvin only, not at any random temperature. Is that clear to you? Okay. Now at any random temperature, what I am saying, probability of finding an electron at energy level EF. What you need to find? You need to find the probability of finding an electron at energy level EF. Now you will say that, sir, this formula is applicable for the energy state, not for energy level. But here you need to find the probability of finding an electron at energy level EF. This is what you need to find at any random temperature, which is not equals to 0 Kelvin. So sir, how you can apply the formula? I can apply the formula if on energy level, on this energy level EF, there is only one state. Then energy level and energy state would be the same thing only, no? Are you able to understand what I am saying? On Fermi level, if there is only one state, that means whatever the electron is found, that will be there on this state only, no? If there are more than one state, let's just say there are two states, and I am saying that probability of finding an electron on this Fermi energy level is 1 by 2. That means probability of finding the electron on this particular energy state will be 1 by 2 into 1 by 3. And here also 1 by 2 into 1 by 3. Why so? Because on this Fermi energy level, on this floor, if some person can be found, that probability is 1 by 2. Now on this floor there are 3 rooms. On this floor there are 3 rooms. So what is the probability of finding the electron, or what is the probability of finding that particular guy in one room? That would be 1 by 2 into 1 by 3, 1 by 2 into 1 by 3, 1 by 2 into 1 by 3. But if I say on this floor there is only one room, and probability of finding a guy on this floor is 1 by 2. So what is the probability of finding the guy on this particular room? That will also be 1 by 2 only, because if he is there on this floor, then surely he will be in this room only. That means if your energy level is only having one state, your energy level is having only one state, then your formula will be working for the energy level as well. Are you able to understand this point? So your Fermi energy level is just an imaginary energy level. It is not a practical energy level. So you will, by default, you will consider that it is having only one state. In the examination as well, let's just say they are calling E as an energy level. Okay. And they are asking you what is the probability of finding an electron at this particular energy level. Or let's just say this question was there in the examination, but in place of state they have mentioned level. So by default you will consider that on this energy level there is only one state. If there are more than one state, then they will specifically mention it. If they are not mentioning it, that means by default you will say level equals to state. But if there are more than one state, they will specifically mention it, and that is known as degeneracy factor. We will discuss that. Okay, so they will specifically discuss it. Okay, they will specifically mention in the question. So here also this formula will be applicable. Why so? Because on one Fermi energy level we will consider that there is only one energy state. Okay. So what will be the formula? 1 upon 1 plus EF minus E minus EF by KT, right? E minus EF by KT, that was the formula, but in place of E we are putting EF. So EF minus EF by KT. Temperature could be anything, but it is not 0 Kelvin. So what you will be getting? 1 upon 1 plus e to the power 0 divided by something. 0 divided by something, what that would be? 0 only. 0 divided by something will be 0 only. So e to the power 0 is 1. So what is that? Answer is getting half. So probability of finding an electron at Fermi energy level at any random temperature is half. So that's why we define this Fermi energy level. Are you able to understand this point? So this can work as a reference for us. At 0 Kelvin, above it everything is empty, below it everything is filled. And at any random temperature, at EF, the probability will be half. Right? So this is how we define our Fermi energy level. The Fermi energy level. The Fermi energy level is an imaginary energy level. It is not practical energy level that electrons can occupy. At 0 Kelvin, all the states below EF are completely filled with electrons, and all the states above EF are empty. At any temperature, the probability of finding an electron at EF is 1 by 2. Now, what I am asking, probability of finding the electron at some energy level which is above EF. Probability of finding an electron at an energy level which is above EF at any random temperature. At any random temperature will be less than 1 by 2. Do you agree to this point or not? What I am saying, energy level which is above EF at any random temperature, what I am saying, E is greater than EF. E is greater than EF, and temperature is anything random. So what you will write down? F of E 1 upon 1 plus e to the power E minus EF by KT. This value will be positive, right? And this is some value. KT will be some value. E to the power something positive. It will be surely greater than 1, for sure. E to the power something positive will be surely greater than 1. You can take any value, or you can just simply draw the graph of e to the power x. No, what will be the graph of e to the power x? At 0 it will throw the value 1. E to the power 0 value is 1. So if in the e to the power, if you are getting anything positive, even if you are getting 0.00001, then also answer will be more than 1. So this value will be more than 1. E minus EF, right, which is positive. Positive divided by something. That means the whole value will be positive. In e to the power, if there is anything positive, then the value will be greater than 1. So this value is greater than 1. This particular value is greater than 1. Let's just say this value is 1.1. So what will be the answer? 1 upon 1 plus 1.1, that would be 2.1. Is it greater than 1 by 2 or less than 1 by 2? It is less than 1 by 2. So at 0 Kelvin, what was the scenario? At 0 Kelvin, the scenario was above EF, probability is 0. Above EF, probability is 0. In the worst case, the probability could be 1 by 2. Basically, the probability will be between 0 to 1 by 2 only. Worst case means, what will be the worst case? The worst case would be that this value becomes how much? This value becomes 1. And when it can become 1? When E is equals to EF. When E is equals to EF, at any random temperature, when E is equals to EF, this will become 1 by 2. So above EF, probability of finding the electron will be 0 at 0 Kelvin. At any random temperature, it will be lesser than 1 by 2. Are you able to understand this point or not? Just the simple mathematics. And we will understand it with respect to Venn diagram as well. Don't worry about that. But are you able to understand the mathematics? If E is greater than EF, this value is positive. KT is also positive. E to the power anything positive would be greater than 1. That means this value is greater than 1. So 1 plus something greater than 1 will be greater than 2. So 1 divided by something greater than 2 would be less than 1 by 2. So probability of finding electron for E greater than EF at any random temperature will be less than 1 by 2. Okay, and for E less than EF, probability of finding an electron will be surely greater than 1 by 2, and it can never be greater than 1, so it has to be less than 1. So are you able to understand this? I will just simply write down in statement what I am writing down. Just here I will write down probability of finding an electron at energy level or at energy state E, which is greater than EF, will always be less than 1 by 2. And probability of finding an electron at energy level or at energy state which is less than EF will always be greater than 1 by 2, and surely the probability cannot be greater than 1. And this is true for any random temperature. T is any temperature where T is any temperature which is not equals to 0. All good? All fine? Now we need to draw the graph. Which graph I need to draw? I need to draw the graph of f of E versus E, where this is my EF. So let's draw it at 0 Kelvin. At 0 Kelvin, how I will draw this graph? So at 0 Kelvin, before EF, probability of finding an electron will be 1. But after EF, the probability of finding the electron will be 0. Let it go like this. So this is the diagram at T equals to 0 Kelvin. Now let's draw it at T equals to 300 Kelvin. Okay. So at at T equals to 300 Kelvin, what will happen? For E less than EF, what will happen? The probability will be greater than 1 by 2. So this point I am calling, this is the probability 1 and this is the probability 1 by 2. Okay. So what will happen? When E is equals to 0, at energy level, what I mean to say is that, let's write down the formula. F of E is equals to 1 upon 1 plus e to the power E minus EF by KT. So what I mean to say is that E is much lesser than EF. E is much lesser than EF. That means this value is very large in negative. E minus EF is very large in negative, because if E is much lesser than EF, then E minus EF will be very large in negative. That means it will be somewhat e to the power minus infinity only. So here the probability will be 1 only. What I mean to say is that if energy is 0 energy, it is not practically possible. But what I am saying is that if your energy level is much below EF, that means EF minus E is very large, because energy, this is your EF and my energy level is much below EF. That means this gap is very large. If this gap is very large, that means E minus EF is very large negative value, because this is at higher level and this is at lower energy level. So E minus EF will be very large negative value. So negative divided by something, that would be negative only, and very negative means e to the power minus infinity. That means e to the power minus infinity will be 0 only. So 1 by 1, that would be 1, and slowly it will start reducing. But you know one thing, that for E less than EF, the probability will always be greater than 1 by 2. That means the graph will reduce, but it will not go lesser than 1 by 2. Are you able to understand this point? So the graph will be reducing like this, and after that it will go somewhat like this. This is how the graph will go. Is that okay for you? Let me draw it again. Okay, is that fine for you? For E less than EF, what I can see, for E less than EF, the probability of finding the electron is always greater than 1 by 2. This is what I have written for E less than EF. If your energy level is below EF, then surely the probability will be greater than 1 by 2. And if your energy level is, or energy state is, above EF, then probability will be less than 1 by 2, which is less than 1 by 2. This point is 1 by 2 only. Okay. And it is pretty obvious as well. What do you mean by that? So let's just say this was your 0 Kelvin, this was your valence band, and this was your conduction band. As you increase the temperature, what will happen? Sir, some electrons from here will go here, and some vacancies will be created here, and some electrons will be here. Sir, initially you said that, sir, this was my EF. Now let's just say, sir, this is only your EF, but what you can see, that what you can see is that above EF as well, now there are some electrons. Previously above EF there was 0 electron. So you said that at 0 Kelvin this is the scenario, that there is nothing. But now, sir, just as you increase the temperature, some electrons from the conduction band is going into the valence band. That means above EF as well you are getting some electrons now. So that means there is some finite probability of finding the electron above EF as well, but it will never be more than the electrons in the valence band, right? So that's why this is the graph, that here the probability will be 1 by 2 and here the probability will be less than 1 by 2. This I am drawing for T equals to 300 Kelvin. Now you need to draw the graph for T equals to 400 Kelvin. Draw it by your own. What I am saying, draw the graph for T equals to 400 Kelvin. How the graph will go? Use the mathematics and use this band diagram as well. Use both of the things. How the graph will go? This is how the graph will go. This will be the graph at T equals to 400 Kelvin. So first understand by band diagram. So this was the scenario at T equals to 300 Kelvin. Now if you increase the temperature more, what will happen? More electrons will go here, more electrons will go here, more electrons will go here. And this was your EF. So probability of finding the electron above the Fermi energy level has increased. Previously there were only 2 electrons, now the electrons are 3. So probability of finding the electron above the Fermi energy level has been increased. But now what is the scenario? Now the scenario is, here the electrons are gone. That means probability of finding the electrons below the Fermi energy level. Previously there were 4, and now just as you increase the temperature at 400 Kelvin, there are 2 only. So probability of finding the electrons below the Fermi energy level has decreased. This is for T equals to 400 Kelvin. Now if I draw for T equals to 500 Kelvin, then what will be the scenario? Then here the probability will keep on decreasing, but after that the probability will keep on increasing. So this will be the graph for T equals to 500 Kelvin. Are you able to understand this point or not? As the temperature increases, the probability of finding the electron above Fermi energy level increases, and below Fermi energy level it decreases. And let's go by the mathematics now. What I will do? I will use the mathematics now. So what is happening? Temperature is increasing. This term is increasing. That means this whole term is going down. E to the power whole term is going down. That means this complete e to the power is going down. 1 upon something is going down. That means this value is increasing. What I am saying is that I am saying E is greater than EF. E is greater than EF. That means this value is positive. E is greater than EF means e to the power something positive divided by kT. Now temperature goes up, so this value goes down. E to the power some value goes down. That means this whole value goes down. That means the whole denominator is going down. And if whole denominator is going down, that means this whole value is going up. So for E greater than EF, the value is going up, the probability is going up. So you can see that with respect to the temperature, it is going up. But for E less than EF, what will happen? For E less than EF, what will happen? For E less than EF, e to the power E less than EF, that means something negative divided by kT. If T increases, for E less than EF, if T increases, what will happen? If T increases, then this value will increase. Then total value e to the power negative total value is decreasing. E to the power negative total value is decreasing. That means what I can say, 1 upon e to the power positive is decreasing. E to the power negative means e to the power minus x means 1 upon e to the power x. So if this value is decreasing, then what will happen? The whole value will go up, no? Because there is a negative sign. So the whole value is going up. So this whole value is going up. That means 1 upon something is going up. What does that mean? The whole value should go down. So you can see that as the temperature increases, the probability of finding the electron is going down. So this was there for T equals to 0 Kelvin, and after that the graph came into action for T equals to 300 Kelvin. Then the graph came into action for T equals to 400 Kelvin. And then the graph came into action for T equals to 500 Kelvin. T equals to 500 Kelvin. So is this graph understandable to you or not? By the Venn diagram, by your simple concept, from whatever you want to understand, it is surely clear to you. Say yes or no. So this has been written in very short line. At higher temperature, occupation probability at higher energy will increase, and while occupation probability at lower energies will decrease. Is that clear to you or not? So all the mathematics I am not going to write down in the notes. That you can write down in rough manner anywhere, like here, if you want to write down, you can write down. But now you are able to understand what is happening. Shall I repeat whatever that we have understood till this point? Okay, Fermi energy level, sometimes it becomes typical for the student if you don't understand it, but you are able to understand it. Fermi direct distribution, which we started from, probability of finding an electron at a particular energy state E is given by 1 upon 1 plus e to the power E minus EF by kT. If E is greater than EF at 0 Kelvin, there will be no electrons, and if E is less than EF at 0 Kelvin, there will be all the electrons. Probability 0, probability 1. Okay, then we draw the diagram for intrinsic, N type, P type. For N type, the Fermi energy level is near to the conduction band, and for P type, the Fermi energy level is near to the valence band, and for intrinsic, it is somewhere in between. Then we got to know that the formula that we derived, the conclusion that we made, that was applicable only at T equals to 0 Kelvin, that above EF everything will be filled and below EF everything will be empty. That is true only for 0 Kelvin. If there is some other temperature, then I have to apply the mathematics. But another thing I get to know is that if your energy level is above EF, then at any temperature the probability cannot be greater than 1 by 2. It has to be less than 1 by 2. Why so? Why so? Because if E minus EF is positive, then positive divided by any temperature will be the value greater than 1. So 1 divided by anything greater than 2 would be less than 1 by 2. And similarly, opposite would happen, that if your energy level is below EF, then at any temperature the probability will be greater than 1 by 2 only. All good? All fine? So this has been written, and this is also one of the conclusion. And then we draw this graph. This graph also we understood that as you keep on increasing the temperature, the probability of finding the electron at higher energy level will increase, and probability of finding the electron at lower energy level will decrease. Okay, so it is decreasing with the increasing temperature, and this is increasing with the increasing temperature. So this is what we have understood. Every single thing is crystal clear to you. Say yes or no. Let's go to the next one. So this you need to let me know, and from here we will make another conclusion. So let's see what is that conclusion. So you find out this particular thing. Probability of finding an electron at energy state E, which is delta E above the Fermi energy level. What does that mean? That means E minus EF is delta E. Energy state E, which is delta E above the Fermi energy level. So this is your Fermi energy level, and this is your energy state E, right? So this is delta E. So what will be my answer? 1 upon 1 plus e to the power delta E by kT. This is the answer, right? What is the formula? 1 upon 1 plus e to the power E minus EF by kT. E minus EF is delta E. So this is what I have written. Usually what will happen is that delta E will be given greater than or equals to 3 kT. Okay. In your examination, 100% this condition will be there. 100%. Surely I am saying that delta E will be greater than or equal to 380. Answer is done. Okay, answer is done. I am just telling one separate thing. This answer is done. I am just telling one more thing. So this will be delta E would be greater than or equal to 3 kT. Let's take the worst case that delta E is equal to 3 kT. So what will be your answer? 1 upon 1 plus e to the power 3 kT by kT. So kT will get cancelled out. Your answer will be 1 upon 1 plus e to the power 3. Now go to your calculator and check the value of e to the power 3. So this e to the power 3 is much larger than 1. What I am saying, e to the power 3 will be much larger than much larger than 1. So if it is much larger than 1, then this one I can ignore, because e to the power 3 is very much larger. Now this e to the power 3 can go upward, so this will become e to the power minus 3. So what is happening here? So your final answer is coming out to be e to the power minus 3. So what is happening here? This gap, basically this particular thing will be greater than or equals to 3. That means this value will be very much larger. E to the power del E by kT will be very much larger than 1. In your examination, this condition will be 100% satisfied. What I am saying, e to the power del E by kT. Since del E is greater than or equals to 3 kT, I am taking the worst case. Then also I get to know that e to the power del E by kT is much larger than 1. That means this 1 can be ignored. So final answer is e to the power minus del E by kT. And what was here del E? Del E was, what I mean to say is that, although this point will again come into action, but still I am saying, what I am saying, it will be nearly equals to e to the power minus del E by kT. Will that be okay for you if I write down in this manner? Because this condition will be satisfied for sure. And what was your del E, if you remember? Your del E was e to the power minus, del E was E minus EF. E minus EF by kT. So probability of finding an electron at a particular energy state E is given by e to the power minus E minus EF by kT. Probability of finding an electron at energy state E. Probability of finding an electron at an energy state E is approximately given by e to the power minus E minus EF by kT. Although all these points will come again, but just here I thought of explaining it, so I explained it. Because e to the power delta E by kT, this value will be very much larger, so 1 can be ignored. So e to the power minus delta E by kT, right? E to the power minus delta E by kT. So what is delta E? Delta E is E minus EF. So probability of finding an electron at energy state E will be approximately given by e to the power minus E minus EF by kT. It is known as Boltzmann approximation. Okay, you know name, you don't need to remember that it is Boltzmann approximation or whatever it is, but you just need to say that this answer is also possible. Well and good. Okay, so this is just I have written, but our answer was this much only. Now what you need to find? Probability of not finding an electron at energy state E, which is delta E below the Fermi energy level. Not finding an electron. Then what I can do? I can find the probability of finding the electron. Then I can, what I mean to say is that if I find the probability of finding an electron at energy state E, which is 0.4. So what will be the probability of not finding an electron? That would be 1 minus f of E, right? So there you. So what I need to find? I need to find the probability of finding an electron, the probability of not finding an electron at energy state E, not finding an electron. So that would be equals to 1 minus probability of finding an electron at energy state E, right? So that would be equals to 1 minus 1 upon 1 plus. Now you let me know what is the scenario here. This is your E and this is your EF, right? Probability of not finding an electron at energy state E, which is delta E below the Fermi energy level, right? So what will be the value of E minus EF? Oh, sorry. Below the Fermi energy level. No, so this is the Fermi energy level and this is the energy state. So what will be the value of E minus EF? That will be minus delta E. Because EF is at higher level, no? Your energy state E is below EF, delta E below. So that means EF minus E is equals to delta E. I should write down EF minus E is equals to delta E. So E minus EF would be equals to minus delta E. So 1 upon 1 minus 1 upon 1 plus e to the power e minus ef by kt. What is the value of e minus ef? Minus delta e by kt. 1 upon 1 plus e to the power e minus ef by kt. E minus ef is minus delta e by kt. All good, all fine. Let's try to solve it. What you will get? 1 plus, or what I can do is that let's solve it. 1 plus e to the power minus delta e by kt. This I am multiplying here. Basically I am taking the LCM. I am taking the LCM, then this goes here and this goes here. Minus 1 divided by 1 plus e to the power minus delta e by kt. Okay, so what will happen? 1 to 1 will get cancelled out. So what you will be left with? This e to the power delta e by kt, in numerator and denominator, what I am doing? I am dividing by e to the power minus delta e by kt. So what I will get? 1 upon 1 plus e to the power delta e by kt. So this is the probability of not finding an electron which is below energy state, which is delta E below the Fermi energy level, not finding an electron. What that is coming out to be? 1 upon 1 plus e, 1 upon 1 plus e to the power delta E by kt, 1 upon 1 plus e to the power delta E by kt. So what do you understand by that? Probability of finding an electron at energy state E, which is delta E above the Fermi energy level, is equals to probability of not finding an electron at energy state E, which is delta E below the Fermi energy level. What do you understand by that? Let's just say this was your Fermi energy level, and there was an energy state E1 here, and there was an energy state E2 here. What was the gap? Let's call this as E1, this as E2. Okay, otherwise you will be getting confused. E1, okay, and this as E2, E2, E2. Yeah. So the gap between E1 and EF is delta E, and gap between EF and E2 is also delta E. So if you are saying that I am finding an electron here, that means that electron would have come from this state only, no? That means if you are saying that I am finding the electron here, that means you will not find the electron here, because EF is right in between. That means above EF if you are finding the electron, that means below EF you are not finding the electron. Are you able to understand what I am saying? EF is the imaginary Fermi energy level, which is your reference point. So above this particular point, if I am finding the electron, that means it would have surely come from here only, no? So if it is already there, that means here there is a vacancy. Vacancy means holes. Holes means not finding the electron. So above EF if you are finding, that means below EF you will not find. So probability of finding the electron above EF will be equal to probability of not finding the electron below EF. But the condition is both should be at the same level. That means it should be delta E above, it should be delta E below. It's not that, sir, this is the energy level E1, this is the energy level E2, and this is your EF. So this gap is, sir, some 1 electron volt, and sir, this gap is some 5 electron volt. So probability of finding the electron will be, if you are finding the electron here, that means you will not find the electron here. No, that is not the condition. Both should be symmetric. Above EF, everything is symmetric. So above EF if I am finding, then below EF I am not finding. This is that I have proved using the mathematics. That's it. And I hope you have understood the mathematics. What I did here was I just divided by e to the power minus delta E by kt. So this became 1, this also became 1, and 1 upon e to the power minus delta E by kt would become e to the power plus delta E by kt. All good? So above EF there is an electron, below EF there is not an electron at the same energy level. So these kind of questions are asked in the GATE examination sometimes. Okay, so let's keep it here. Let's keep this diagram here, this diagram also, this diagram also. So if they are asking this question, probability of finding an electron at an energy state which is 0.05 electron volt above the Fermi energy level is given by 0.4. So what you will do, you will make the Fermi energy level above the Fermi energy level, which is 0.05 electron volt above the Fermi energy level. This is your Fermi energy level, this is your energy state, let's call it E1. So here the probability is 0.4. Using this information, determine the probability of not finding an electron at energy state 0.05 electron volt below the Fermi energy level. So PE2 they are asking, not finding an electron. So what that would be? That would be 0.4 only. They could have asked they could have asked the value of finding the electron. Probability of finding the electron, that would be 0.6, because this gap is same only. So how will you solve it? How will you solve this particular question? If you don't know, if you don't remember anything, sir, this is the straightforward question is coming in front of me in the examination hall. How will I solve it, sir? So probability of finding an electron at energy level E1, that would be 1 upon 1 plus, it is E minus EF, E minus EF. Since it is 0.05 above, so here I will use the positive sign, divided by KT. So this is the value of f of E1, which is given as 0.4. Sir, what I need to find? I need to find the value of, this is my final answer. This is what I need to find. What I need to find, sir? Probability of not finding an electron at energy state E2. Sir, that would be equals to this thing, sir, and that would be equals to one plus e to the power sir, E2 is below EF, so E2 minus EF would be minus 0.05 divided by KT. So if you take this downward, or you can say I am dividing by e to the power minus 0.05 divided by KT in the numerator and denominator. So what I will be getting? I will be getting 1 upon 1 plus e to the power 0.05 divided by KT. This value is similar to 0.4 only. So sir, this answer and this answer will be the same. So this will be my answer. Probability of not finding the electron. Okay, so this is the final answer. Probability of not finding the electron at energy level or at energy state E2, which is 0.05 electron volt below the Fermi energy level. Okay, so this concept is also useful in solving the problems, but even if you don't remember this concept, then also you will be able to solve the problem by simple concept, right? Now I can draw the graph. What I am drawing? I am drawing the f of E versus, not f of E, I should not say f of E. This axis I am not telling what it is, I am just telling that this is your energy. So this graph I am saying that at a particular temperature, this is the graph of probability of finding the electron at a particular energy state E, at a particular energy state E. So this is the graph of f of E. Then what this will be? This will be the graph of 1 minus f of E, because if this value is 1, then this value is 0, and if this value is 0, then this value is 1. And what will be this value? This value will be simply equals to half. So this is the graph of probability of finding the electron at an energy state E, which is below EF, or it could be above EF as well. What I mean to say is that probability of finding an electron at energy state E, which is above EF by delta E amount. What I mean to say is that this is the value of E. So this is your delta E amount. Okay. Now I need to find out the probability of finding an electron which is here at energy state, which is here. This is also delta E. This is your energy state E1. This is your energy state E2. Here what we saw, here we saw that our energy state E1 was above EF and E2 was below EF. But this formula is applicable for opposite case as well. What I mean to say is that this is my EF and this is my E1 and this is my E2. Now if I know that I am having an electron here, that means this electron will not be here. What I mean to say is that both gaps are same, delta E and delta E. What I mean to say is that if I know the probability of finding an electron at energy state E1, which is delta E below the energy state EF, then I can tell you that what will be the probability of not finding an electron at energy state E2, which is delta E above the EF. symmetricity is there, no? This is what I am saying. This graph and the other graph, it will be this graph, which is the probability of not finding an electron. So for this particular graph, for the white graph, if you are standing here, then this will be your answer. And for this, for this red graph, this will be your answer. And for this white graph, if you are standing here, then this will be your answer. So both red and white graph are giving you the same answer. Both red and white graph are giving you the same answer. One is telling about the probability of not finding the electron, and one is telling about the probability of finding the electron. One is talking about energy level E1 and one is talking about energy level E2. So E2 is below EF by delta E, E1 is above EF by delta E. So probability of finding the electron at energy level or at energy state E1, which is delta E above the EF, is equals to probability of not finding an electron at energy level E2 or at energy state E2, which is delta E below the EF. Shall I again repeat the statement? Or opposite is also true. What is the opposite? The probability of, let's talk about this particular energy level. What I am saying, let's talk about this particular energy level. This is the energy level E2, not E2, let's call it E3, and this is the energy level E4. Okay, and both are giving you the same results. Both graphs are giving you the same results. So repeat the statement. What I am saying, this is your delta E1 or delta E2. Let's call this as delta E1, and this is also your, this will be your E4. So gap between E4 and EF is also delta E2 only, and let's call this as delta E1, delta E1. So probability of not finding an electron at energy state E3, which is delta E above EF, will be equals to probability of finding the electron at energy state EF, which is delta E2 below EF. The same scenario that I explained here. That if I know above EF at a particular state there is an electron, that means below there will not be any, that there will not be any electron. And if I know that below that there is an electron, that means above that there will not be any electron. Is that clear to you or not? Very simple thing. Just I can say that the graph is like symmetry. Above a particular energy level, finding an electron, probability of finding an electron will be equals to below a particular energy level, not finding an electron. So in the statement, these lines could be written and they can ask you whether the statement is correct or not. So forget about all these concepts. You don't remember the graph. What you can do is that you can simply derive it there using this thing. If you don't remember the statement, I also recommend not remembering any statement. Just you should know that I have studied this kind of concept, that above EF at a particular energy level, below EF at a particular energy level, something is there, some relation is there, and that I can derive in the examination based on the given statement. So in the examination, if this statement is written, the probability of finding an electron at energy level delta E above the Fermi level is equals to probability of not finding an electron at the same energy level delta E below the Fermi level. And opposite is also true. What does that mean? The probability of not finding an electron at energy level delta E above the Fermi level is equals to the probability of finding an electron at same energy level delta E below the Fermi energy level. So here if I apply not finding an electron, and here if I ignore this not, then also the statement will be true. So two statements could be written in the like which of the following statement is true? Statement 1, statement 2, statement 3, statement 4. So it could be MSQ, you need to mark the correct statement. Is that clear to you or not? So you will just draw the diagram. There what you will do, you will draw these two diagrams. So this diagram I will draw, this diagram I will draw, so this diagram I will draw, and in between, sir, I will make EF and EF. Then I will say that, sir, that here if electron is there, that means here electron will not be there, and if here electron is there, here electron will not be there. That's it. So probability of finding an electron which is delta E1 above the Fermi energy level, that would be, if that is something that I know, then the probability of finding an electron at energy state E2, which is delta E1 below the Fermi energy level, that would be the same. Probability of not finding the electron. Not finding the electron, finding the electron. Okay, here also finding the electron, not finding the electron. So statement and everything is clear to you, right? I don't need to explain it more. All good, all fine. Let's go to next topic, which is very important. Probability of finding an electron in the conduction band. Now in the conduction band, if I am saying that I am having an electron, what does that mean? I am talking about free electron. That means I am talking about the charge carrier. So what I am saying, probability of finding a charge carrier in the conduction band. Probability of finding a charge carrier in the conduction band, because when I am saying that there is an electron in the conduction band, that means that is free to move, and if that is free to move, that is known as charge carrier. So this is nothing but our charge carrier. Charge carrier. Okay. So what that would be equal to? Probability of finding an electron in the conduction band. Now you will say that, sir, this is the energy of the lowest state of the conduction band. EC is the energy of the lowest state of the conduction band. Then sir, this energy EC1 will be slightly greater than EC, and sir, this energy will be EC2, which will be slightly greater than EC1 and slightly greater than EC, and sir, this will be EC3. So sir, all these energies are different. There will be slight gap. Let's just say if EC is at 1 electron volt, then EC1 will be at 1.01 electron volt. This would be 1.02 electron volt, and this would be 1.03 electron volt, because this is how the diagram is made. No, as you go upward, the energy will be increasing. But in our calculation, we will assume that all are having the same energy. Nearly they are having the same energy. So what I am writing down for our calculation, for ease of calculation, this is something that is considered. So probability of finding an electron at energy state EC, that would be equal to probability of finding an electron in the conduction band. Is that okay for you or not? Because in the conduction band there are a lot of states, and all states are having different energy. In the conduction band there are a lot of states, all states are having different energy, but we are saying that all are having the same energy, that is EC only. That means what you will consider is that in conduction band only there is one state, that is EC. So probability of finding the electron, probability of finding the electron at energy state EC will be given by 1 upon one plus e to the power EC minus EF by KT. Now what did I tell you? That sir, this EC minus EF by KT would be greater than 3 KT. What I mean to say is that in our case that is known as non-degenerate semiconductor. So in the end of this video, I will again explain what do you mean by non-degenerate semiconductor, but I hope you already remember non-degenerate and degenerate. What do you mean by non-degenerate? That means their doping is moderate, and degenerate means doping is very high. High doping, you remember in first or second video I explained this, and here there is moderate doping. So basically what I mean to say is that this value will be very high in our case. That means EC minus EF will be sufficiently large enough. So e to the power 3 is coming, that I told here in this analysis. Here e to the power 3 would come. So if e to the power 3 is coming, that means this value will be sufficiently large. If this is sufficiently large, then you can ignore the 1. If I can ignore the 1, then this can go upward. So the similar thing I am going to write down here. Okay. So it can be approximately equals to, in our case, this is your approximation, it can be approximately equals to e to the power EC minus EF by KT. There you go. This is known as Boltzmann approximation or Boltzmann statistics. Okay. So this formula we will be using. This formula will be using, not this formula. This also I can use, but this will take more time in the calculation. So this formula we will be using. Probability of finding an electron at energy state EC, or you can say probability of finding an electron in the conduction band. That would be equals to e to the power minus EC minus EF by KT. All good, all fine. Now what we are asking? Probability of finding an hole in the valence band. So holes are made only in the valence band, right? Holes are made only in the valence band. in the valence band if there are holes. What does that mean? That means electrons are not there, because how the holes are made? Holes are made because electron went to the conduction band. That's why holes are made, no? Are you able to understand this point? So generation of holes is there because electrons are gone. That means what I can write down? Probability of finding a hole in the valence band is equals to probability of not finding an electron. Probability of not finding an electron in valence band. Say yes or no? And that would be equals to 1 minus probability of finding the electron in the valence band. This is the probability of finding the electron in the valence band. Probability of finding the electron in the valence band, that would be equals to 1 minus f of EV. What is f of EV? F of EV is probability of finding the electron in the valence band. Say yes or no? All good? So 1 upon 1 plus 1 minus 1 upon 1 plus e to the power EV minus EF by KT. If I solve it, what I will be getting? This will go here, this will be minus 1. Basically, I will take the LCM now, right? I will take the LCM. So e to the 1 plus, what I will be getting? 1 plus e to the power EV minus EF by KT minus 1 divided by 1 plus EF minus EF by KT. So this and this will get cancelled out. What you are left with? So basically 1 and 1 is getting cancelled out, so I am just removing it from here. I am just removing it from here. Okay. So what I can do now? I can divide by the same in the upward side and in the downward side. So if I divide by this particular thing, e to the power EV minus EF by KT, so what I will be getting? 1 here divided by e to the power EV minus EF by KT divided by e to the power EV minus EF by KT, that would also be 1 plus e to the power, what will happen to this particular thing? 1 is divided by e to the power EV minus EF by KT. So what you will be getting? Minus EV minus EF by KT. Okay. All good. Now you know that where will be your Fermi energy level? Fermi energy level will be above the valence band. If you go to the first second page, I told you for the semiconductor, for the p-type semiconductor or n-type semiconductor or intrinsic semiconductor, whatever you take, basically the Fermi energy level is between the conduction band and valence band. For any semiconductor, the Fermi energy level will be between the conduction band and valence band. Right? In our calculation, it will always be between conduction band and valence band. So it will always be between somewhere between conduction band and valence band. That means it will be somewhere here, because if this is your valence band, then this will be your conduction band. So Fermi energy level will be somewhere here. So EV minus EF will be negative. EV minus EF will be negative. Say yes or no? EV minus EF will be negative because EV is at lower energy level, EF is at higher energy level. So E minus negative. So what it has become? E positive divided by KT. And I told you this positive value will be greater than 3 KT. What I mean to say is that simply EF minus EV will be greater than or equals to 3 KT. Here also I will write down the same thing. What I will write down? That I know that EC minus EF will be greater than or equals to 3 KT in our calculation for sure. And similarly here as well, who will be at the higher level? Who will be at the higher level? EF will be at the higher level. So here also I can write down that EF minus EV, not here, I should write down here. Here I am putting it out that EF will be at higher energy level. So EF minus EV will be greater than or equals to 3 KT. That means this gap will be greater than or equals to 3 KT. Okay, fine. So this value will be negative. Basically minus EV minus EF by KT is written. So can I write it down in this manner? EF minus EV by KT. EF minus EV by KT. because already there was a negative sign. When I took it downward, there was already a negative sign. So that negative sign I have taken inside. So EV minus EF minus EV by KT I can write down. Do you agree to this point? Right? How it came? You will agree to this point. Now EF minus EV is greater than 3 KT. Then what I can do? One I can ignore. Then what will happen is that probability of not finding an electron in the valence band is coming out to be what I am saying. Probability of not finding an electron in the valence band, or probability of finding an hole in the valence band is coming out to be, this part will go upward. So e to the power minus EF minus EV by KT. Don't worry, I will tell you a trick to remember the formula. Don't worry about that. You don't need to worry about anything. I will surely tell you the trick to remember. So probability of finding a hole, probability of finding a hole in the valence band is given by e to the power, approximately it is given by e to the power EF minus e to the power minus EF minus EV by KT. So two formula we have got, this formula and this formula. One was probability of finding the electron in conduction band. Probability of finding the electron in the conduction band. So roughly I am writing down e to the power something was there, and probability of finding the holes. This was for the electron and this was for the hole in valence band. That was e to the power something. So always you need to remember e to the power minus will come. Now here divided by KT would come and here divided by KT would come. The confusion will be here, sir. EC minus EF or EF minus EC. Just think about it. This is your EC. Where will be your EF? And this is your EV. EF will be somewhere between EF and EV. So EC will be greater than EF, no? EC will be greater than EF. And let's just say if I write down a negative value here. If I write down a negative value here. So what it will become? E to the power positive divided by KT. E to the power positive. That would be e to the power positive divided by KT. That would be greater than 1. That means probability of finding the hole is greater than 1. Probability is greater than 1. Is it possible? No. That means what you will do, e to the power minus, then something inside will be positive only, sir. Something inside will be positive only. Now what will be positive? EC is at the higher level than EF. So EC minus EF. EF is the higher level than EV. So EF minus EV. So you can see the formula. E to the power minus EF minus EV by KT. So what you will do, sir, e to the power minus, then which is at the higher level? EF is at the higher level. So EF minus EV by KT. Sir, e to the power minus, which is at the higher level? Sir, EC is at the higher level. So EC minus EF by KT. Will you be able to write it down? Probability of finding an electron in the conduction band is given by this. Probability of finding an electron in the conduction band is given by this, and probability of finding a hole in the valence band is given by this. Probability of finding a hole in the valence band is given by this. E to the power minus EF minus EV by KT. All good, all fine. Everything is crystal clear to you. Okay. Now there is something called effective density of states. So you can see here. What did I tell you in the first lecture? As you go higher in the conduction band, the density of the state increases. That means here the states will be very near and here the states will be very far away. So basically in the conduction band, these many states are there, right? But here the density is more. Basically if I cover the distance of, if I cover a volume of 1 centimeter cube, then here I am getting 4 states. But if I cover the volume of 1 centimeter cube, here I am getting only 3 states. So here the density of state is more, here the density of state is less. But total I know that total 7 states are there. So what they did, they made something called effective density of states. Effective density of states. That means effectively I am telling that in the conduction band these many states are there. What I mean to say is that as you go higher in the conduction band, the density of the state will increase. That means at the higher level more states will be there, at lower level there will be lesser state. Similar thing happen in the valence band as well. As you go lower in the valence band, the density of state increases. As you go lower in the valence band, the density of the state increases. That means here in 1 centimeter cube, you are getting more states, and here in 1 centimeter cube, you are getting lesser state. So I need to define some effective number that effectively these many states are there per unit volume. So what you can say, sir, 7 states are there in 2 centimeter cube. So you can say that, sir, effectively I am having 3.5 states in per centimeter cube. 3 was there in 1 centimeter cube, 4 was there in 1 centimeter cube. So effectively you find out some average value. This is not how it is calculated. I am just telling the way to understand that what is the meaning of effective density of state. So in the conduction band, as you move upward, the density of the state will increase, and in the valence band, as you move downward, the density of states will increase. So there is something called effective density of states. So that will be a fixed number, that they will be giving 2 into 10 to the power 20 centimeter cube inverse. That is the value of effective density of states in the conduction band, and that is shown by Nc. So effective density of states in the conduction band is given by Nc, that is equals to 2 into 10 to the power 20 centimeter cube inverse. That means you will say that in the conduction band these many states are there. Okay, and similar thing can happen for valence band as well. Okay, all good, all fine. So this is what is written, effective density of states. No need to worry about that too much. Just you need to understand that it is like the number of floors available. So number of rooms available or floor you can say, because these are the states only, no? These are all the states. So number of rooms available, that is your effective density of states. That's it. So as you move higher in the conduction band, the density of the states increases. As you move lower in the valence band, the density of state also increases. To simplify the calculation, we define effective density of states, which represents the total number of energy state per unit volume in the conduction band or valence band that are effectively available for the electrons and holes to occupy. It essentially tells us how many electrons can occupy the conduction band and how many holes can occupy the valence band at a given temperature. That means for the electrons to occupy, these many floors are available, and for the holes to occupy, these many floors are available. So you understood the complete theory that has been written. Okay, so effective density of states for the conduction band, in the conduction band is shown by Nc, and effective density of states in the valence band is shown by Nv. Conduction band is always related to electrons and valence band is always related to holes. Electron means free electrons, and this is related to holes, right? So this Nc is proportional to effective mass of electrons to the power 3 by 2 and temperature to the power 3 by 2. So collectively what I can write down? Collectively I can write down that Nc is proportional to effective mass of electron multiply with temperature to the power 3 by 2. You need to remember it, not very tough to remember. Okay, the density of states in the conduction band is proportional to effective mass of electron to the power 3 by 2 and temperature to the power 3 by 2. And what about the holes? Sorry, what about the density of states in the valence band? So Nv will be proportional to, when I say valence band, it is related with holes. Here I am writing down N, so here I will write down P to the power 3 by 2, temperature to the power 3 by 2. So Nv is collectively proportional to Mp to the Mp star into T to the power 3 by 2. So mass, effective mass and temperature, power 3 by 2. I don't think it is very tough to remember. I hope it will be easy for you to remember. So collectively what I can write down, Nc is equals to, if I remove the proportionality sign, what I will get, Nc naught Mn star T to the power 3 by 2. And Nv will be equals to Nv naught, if I remove the proportionality sign, then Mp star T to the power 3 by 2. So this you will be able to remember, say yes or no. Nc is equals to Nc naught Mn star T to the power 3 by 2. Nv equals to Mv naught Mp star T to the power 3 by 2. Okay, very simple. The density of state in the conduction band is proportional to Mn star to the power 3 by 2 and temperature to the power 3 by 2. Density of state in the valence band is proportional to effective mass of holes to the power 3 by 2 and temperature to the power 3 by 2. All good, all fine. Let's solve a mathematics question. This question is of mathematics. Okay, in an apartment there are 100 rooms. In an apartment there are 100 rooms. Finding the probability of finding a person in a given room is 0.3. How many total people are expected to be in the apartment? Total number of people. Total number of people. What they are saying, 100 rooms are there. Let's take 10 rooms only. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Probability of finding a guy in a room is 0.3. So a room will be occupied with the person. What is that probability? That probability is 0.3. So there are total 100 rooms. In one room, it is probability that 0.3 guy could be existing. So in 100 rooms, how many guys could be existing? 30 guys. Very simple thing, no? 100 into 0.3. Why you took mathematics, sir? Because of this. What we need to find? We need to find that total number of electrons or holes per unit volume in a semiconductor. Any random semiconductor, it could be intrinsic, it could be extrinsic, it could be n-type, p-type, whatever it is. So whenever I say electrons, that means I mean free electrons, and whenever I say holes, that means it is holes only. And electrons are found in the conduction band and holes are found in the valence band. The effective density of states in the conduction band is given by Nc. The effective density of states in the valence band is given by Nv. Probability of finding the electron in the conduction band is given by f of Ec. Probability of finding an electron in the conduction band is given by f of Ec. And probability of not finding an electron, or you can say probability of finding a hole in the valence band, is given by 1 minus f of Ev. Okay, so this is what is written. Given that effective density of states of conduction band is Nc, effective and valence band is Nv, the probability of finding an electron in the conduction band is f of Ec, and probability of finding a hole in the valence band is 1 minus f of Ev. So there are total Nc rooms available. The probability of finding an electron on one room that is having an energy of Ec, that probability is f of Ec. So what will be the probability of, what will be the total number of electrons? Again, just try to relate this particular thing with this example. There are Nc rooms available. On one room, finding the electron probability is f of Ec. That means how many total number of electrons would be there? So that number of electrons would be Nc into f of Ec. Say yes or no? Are you able to understand this point or not? There are total Nc rooms available. In these Nc rooms, there are different energy levels. There are different energy states. If this is having an energy of Ec, what I am saying is that if this is having an energy of Ec, then this will have energy of Ec1, Ec2, Ec3. But what we are assuming is that all are having the same energy. So probability of finding an electron in Nc, probability of finding an electron in Ec room is something that is known as f of Ec. And total, like this only, total how many rooms are available? Nc rooms are available. So how many total number of electrons would be there? Nc into f of Ec. Are you able to relate with this particular example? Surely you are able to relate, right? So total number of electrons per unit volume will be, this will also be mentioned in per unit volume, okay? This will also be mentioned in per unit volume. So they will also have the unit of centimeter cube inverse. So per unit volume, these many rooms are available. In one room, finding an electron probability is f of Ec. So what will be the total number of electrons? That will be Nc into f of Ec. So that would be equals to Nc. Now f of Ec you need to write down. How will you write down? Sir, I know that e to the power minus. Now who will be at the higher level? Sir, Ec will be at the higher level. Now you go to any course, anywhere you go, read any textbook, the derivation of this particular formula is very, very complex. You would see they would do some integration, this thing they will introduce, that thing they will introduce, they will spend 2 hours, and there they will have to write down that using higher order mathematics you will get the final expression. But everything we ignored. Just we build our intuition. Just we understood that how we can write down this formula. Just by pure intuition we are doing it. How I started? I started with f of Ec. You did not even know, sir, what we are doing here. Why you are finding the probability of finding an electron in the conduction band. Then you find out the probability of finding a hole in the valence band. Sir, I don't know why you are doing so. Then sir, suddenly you told about effective density of state, and suddenly sir you took a mathematical problem. Now all these 4 slides combined, everything is making sense here. I could have directly written down this formula, or I could have used higher order mathematics, and there I would have said that you need to understand this mathematics on your own and then get the final answer. But now you have understood the flow, right? Effective density of states in the conduction band and in the valence band. Probability of finding a electron in the conduction band is f of EC. Probability of finding a hole in the valence band will be 1 minus f of EV. So here what I will write down, total number of states available are n of V. In one state, probability of finding a hole is 1 minus f of EV. So total number of holes per unit volume will be NV into this value we already know. Probability of finding holes. Sir, what I will write down, sir, e to the power minus. Sir, what I need to write down, positive value. So EF is at the higher level than EV. So EF minus EV by KT. There you go. Okay, you understood this slide in a very good manner. So let's write down the summary of the formula that we have understood till now. So you don't need to remember anything from the previous analysis that we have done. Just these 5 formula you need to remember and your job will be done. Just only these 5 formula. Okay. So probability of finding an electron at energy state E is given by 1 upon one plus e to the power E minus EF by KT. And I know that in our case it will be approximately equals to this thing, right? Now what is this? Probability of finding an electron in the conduction band. Probability of finding electron in conduction band, that is given by e to the power, yeah, so how will you write down? E to the power minus, now sir, EC is at the higher level or EF? EC is at the higher level, so EC minus EF by KT. And here I will write down probability of finding hole in valence band. So that would be equals to e to the power minus, sir, who is at the high level? EF is at the high level. So EF minus EV by KT. Total number of electrons, total number of holes. So NC into this probability, e to the power, sir, EC at the higher level, EC minus EF by KT. And here NV e to the power, sir, EF is at the higher level, EF minus EV by KT. Okay. Sir, NC is equals to NC naught Mn star T to the power 3 by 2. Sir, NV is equals to NV naught MP star T to the power 3 by 2. That's it. This is the only formula you need to remember, and you will be able to solve all the problems. 99.95% of the problems you will be able to solve from these formula only. That's it. And people feel that, sir, in this topic there are a lot of formula. Do you really think that any formula you need to mug up? No. Anything you need to mug up? No. Every single thing in EDC I am explaining with pure intuition. Along with that, there are formulas as well. With the formula as well, you can understand. So do you really think that I need to mug up any single thing? And you watch other series, and you watch other notes, you watch other lectures, and how people apply the formula. This formula came, this question came, this formula you apply. No. We will understand the meaning, and this is the meaning, right? Okay. Here NC note. Now what we will find out? We will find out the position of Fermi level for intrinsic semiconductor, for n-type semiconductor, and for p-type semiconductor. So for intrinsic semiconductor, there is a specific name of the Fermi level that is known as intrinsic Fermi level. Okay, there is a specific name of the Fermi level that is known as intrinsic Fermi level. So for the intrinsic semiconductor, whatever the Fermi level that you are getting, this is the conduction band, this is the valence band, and somewhere here you will get the Fermi level that is known as intrinsic Fermi level. Okay, so we will find out its position. So for intrinsic semiconductor, what do you know? N is equals to P is equals to Ni. Number of electrons is equals to number of holes is equals to intrinsic carrier concentration. So Ni, let's ignore it as of now. N equals to P I need to put. What I need to put? N equals to P. So what is N? Nc multiply with e to the power, sir, here positive number should come. That is equals to Nv e to the power, sir, here also. Sir, here also positive number should come. Right? Now what I am doing is that this Nv I am taking here and this part I am taking here. So Nc by Nv I am getting here. Here what you are getting? Ev minus Ef. This is your Ev minus Ef by kT divided by e to the power Ef minus Ec by kT. Right? Now what can happen is that this part can go upward. So e to the power Ev minus, this part is going upward. So this is positive, so this became negative. So Ev minus 2Ef minus plus Ec divided by kT. Did you understand this part? Right? E to the power Ev minus 2Vf plus Ec divided by kT. This part is going here. Simple mathematics, nothing else. You should be doing it on your own. Okay. So now e to the power, this e to the power something, this e goes here. So what it will become? It will become ln. So ln Nc by Nv is equals to Ec plus Ev, and this kT, if ln goes here, then what it will become? Ec plus Ev minus 2Ef divided by kT. So I am directly multiplying this kT here. Okay, I am directly multiplying this kT here. So now 2Ef goes here, 2Ef goes here, and in place of Ef what I can put? Intrinsic Fermi level, because we are finding it for intrinsic carrier concentration, right? Sorry, intrinsic semiconductor. So here I can put EFI. So 2EFI is equals to EC plus EV minus KT ln NC by NV. So what you are getting? EFI is equals to, let's write it down on the next page. EFI is equals to EC plus EV by 2 minus KT by 2 ln NC by NV. This formula we have got. Again, the only formula I am asking you to remember, which is this. Okay, what I am asking you to remember? EFI is equal to EC plus EV by 2 minus KT by 2 ln NC by NV. What do you understand? Let us say, sir, this is EC and sir, this is EV. So this is EC and sir, this is EV. Let us say this is at a 3 electron volt and this is at 4 electron volt and this is at 1 electron volt. So what will be the mid value of this? What will be the right mid, like right in between? What will be the mid value? Sir, 4 plus 1 divided by 2. That would be, sir, 2.5. So this will be the mid value. That means, sir, EC plus EV divided by 2, because 2.5 above 1, this gap is 1.5 and this gap is also 1.5, because 4 minus 2.5 is also 1.5. So this is the midpoint. So what is the midpoint? Sir, midpoint is EC plus EV by 2. So this is the midpoint. So this is known as E mid gap energy. This is known as E mid gap minus KT by 2 ln NC by NV. So sometimes what they can ask in the questions, that in your intrinsic semiconductor, how much your Fermi energy level, is far away from mid gap. Like basically, what is the gap between the mid gap and intrinsic Fermi level? That would be equals to KT by 2 ln NC by NV. So this formula you need to remember: EC plus EV by 2 minus KT by 2 ln NC by NV. Now special cases we can take, or by default cases also we can take, like case 1, which is known as by default as well. By default means if NC and NV are not mentioned. Okay, so case 1 is NC equals to NV. Or what you can say? Or I can say that Mn star is equals to Mp star. Because if Nc is equals to Nv, what does that mean? That means that, sir, Mn star, no, this will have different constant, no, Nc node, and this will have different constant. What I was about to say is that, sir, this thing would be there, no, Mp star. So I would say temperature and temperature will get cancelled out, and but this constant could be different, Mn star, Mp star. So if Nc and Nv are equal, then Mn star would be equal to Mp star, but not necessary, because this constant could be different. So either this condition is given or this condition is given. If this condition is given or this condition is given or this condition is given, then what you will do? Look, if this condition is also given, no, then also you will consider that, sir, these constants are equal only. Basically, either they will not mention Nc and V. If they will mention, they will not, those will not be equal. What I mean to say is that in the questions, what will happen is that Nc and V, either it will not even be mentioned, Nc and V will not even be mentioned. If it is not mentioned, you will take Nc equals to Nv. That's it. And if it is mentioned, they will not be equal. Then you will have to find out the value. But if both are equal or not even mentioned or not mentioned or not mentioned, then what you will do? Sir, my Fermi energy level will be right in between. So your intrinsic Fermi level most probably will be in between only. Is that okay for you? Okay. Well and good. And now what if Mn star and Mp star are mentioned? What I am saying, case 2, Mn star and Mp star are given. So sir, your EFI would be equals to EC plus EV by 2 minus KT by 2 ln. Sir, this Nc would be equals to, sir, Nc naught Mn star T to the power 3 by 2. And sir, this Nv will be equals to Nv naught Mp star T to the power 3 by 2. So temperature would be same. This also I will have to consider same only, because constant value they are not mentioning, same only. Okay, this is also gone. What I am left with? Mn star and Np star to the power 3 by 2. So Mn star divided by Mp star to the power 3 by 2, right? So what you are getting from here? From here what you are getting? EFI is equals to EC plus EV by 2 minus KT by minus 3 KT by 4 ln Mn star divided by Mp star. EC plus EV by 2 minus 3 KT by 4 ln Mp star divided by Mp star. So do you really think that you need to mug up this formula? No, you are not mugging up the formula. Only formula that you are remembering is EC plus EV by 2. That means most probably it should be in the mid gap. But if Nc and V are not mentioned, then the formula will be mid gap minus KT by 2 ln Nc by Nv. There is only this formula which is having KT by 2. Otherwise, all the formula will have simply KT. Only one formula is having KT by 2. Okay, so EC plus EV by 2 minus KT by 2 ln Nc by Nv. Not very tough to remember, say yes or no, right? So how I can show it? So this will be your conduction band and this will be your valence band, and somewhere in between you will get your Fermi energy level. अरे यार क्या कर रहा हूँ मैं? Conduction band, valence band. So by default I will consider that it is right in between, right in the middle. It is right in the middle. By default I will consider this. This is your EFI. And one thing you know, what do you know? That Mp star is usually more than the Mn star, right? What I am saying, Mp star, effective mass of holes, is more than the effective mass of electron. Usually, not always, usually this is the scenario, no? That effective mass of holes will be more than the effective mass of electrons. So this value will be more. Usually, again in the question anything could be given. So if this value will be more, so ln, let's just say 1 by 2, ln 1 by 2 will be negative. So this value will be negative. So eventually this sign will become positive. Are you able to understand what I am saying? We will solve with respect to question. With respect to question, you will be able to solve. But if you are just able to visualize it, then MP star would be more. If it is more, let's just say it is 1 by 2, then ln 1 by 2 will be a negative value. So this will become positive. That means in the mid gap, something is being added. In the mid gap, there is something that is being added. That means Fermi level will go above the mid gap. So Fermi level in the intrinsic semiconductor as well will be more nearer to the conduction band than the valence band. Usually, it is the usual case. But ideally what we will take, it is right in between, because we will take that NC equals to NV. Say yes or no. Okay. So ideally we will take NC equals to NV, but usually what happens is that effective mass of holes are more than the effective mass of electrons. Then this scenario can come into action. But from this slide, what is the conclusion that you have made? N is equals to P is equals to Ni. Then from there we derived this very simple derivation. The intrinsic Fermi level is coming out to be EC plus EV divided by 2 minus KT by 2 ln NC by NV. So you expected it to be right in between. It is coming in between only, but some offset is there. You can call it offset. That means it will be either above the middle gap or it will be either below the mid gap. So that offset is KT by 2 ln NC by NV. There is a negative sign. Don't forget this negative sign. Then you can put down this formula and you can get this value. Okay. So this was about our intrinsic semiconductor. In the intrinsic semiconductor, the Fermi level is in between the conduction band and valence band. Let's go to our N-type semiconductor. So Fermi level of N-type semiconductor is known as EFN. Okay. Fermi level of N-type semiconductor will be known as EFN. So in N-type semiconductor, what is the number of electrons you are having? E to the power EC minus EF by KT. But since we are talking about N-type semiconductor, so I am putting EFN by KT. Okay. So what you will be getting? This NC I can take here, and then I can take ln. So what I can see here is that ln NC by N is equals to EC minus EFN. Did you understand what I did here? No. N by NC, right? And this e to the power goes here, so this become L. Then this KT, then here what will be the scenario? Minus of EC minus EFN by KT. Then this KT can come here, this KT can come here. So this KT is coming here. Then this negative sign I can take this side, this negative sign I can take this side. Is that okay for you? This is like minus 1. So it can go as ln to the power minus 1. Basically, ln A is equals to minus ln 1 by E. Do you agree to this point? So if I need to erase this negative sign, whatever the negative sign is there, if I need to erase this negative sign, what I need to do? NC by N, right? So EC minus EFN will be equals to KT ln NC by N. So when I am doping, I will make sure that the number of electrons, when I am doping, I will make sure that number of electrons never go above the effective density of states. Why is that so? Because if this value goes above, let's just say this value was 4 and below value was 8. So what you are getting? ln 4 by 8, that would be ln 1 by 2. That is equals to minus ln 2. So this value will come out to be negative. If this value is coming out to be negative, what does that mean? That means EFN is at the higher level and EC is at the lower level. So always we will make sure while doping that NC will be greater than N. If NC is greater than N, then what will happen? This value will be positive. That means this gap will always be positive. So what do you understand? What do you understand? This was my conduction band. This was my valence band. Conduction band and valence band. So where will be your Fermi level? That would be near to the conduction band. Why so? Why is that so? Because if you increase the doping, if I increase the doping, then what will happen? Number of electrons will increase. This value will increase. If this value increases, if N increases, then this whole value decreases. If N increases, this whole value decreases. If this whole value decreases, then ln value also decreases. This whole value decreases. And if this whole value decreases, then this whole value decreases. That means EC minus EFN decreases. So more doping means lesser gap between conduction band and Fermi energy level. What I am saying, more doping means this value increases, so this value decreases. If this decreases, then this decreases, and then whole value decreases. So more doping, more donor atoms means this value is lesser. That means this gap is lesser. So more doping means you are moving more towards the conduction band. That means the gap between the conduction band and the Fermi energy level is lesser. So what do you understand here? Let's just say if this is my doping of ND1, this is my doping of ND1, then this is my Fermi energy level. And if my Fermi energy level is here for the doping of ND2, then which doping will be higher? ND1 or ND2? ND2 will be higher, because higher doping means your Fermi energy level is near to the conduction band in case of n-type semiconductor. So in case of n-type semiconductor, you get the Fermi energy level near to the conduction band. It is not in the middle. It is near to the conduction band, and it is far away from the valence band. All good? All fine? So this is the formula of EC minus EFN. The same formula you can get from the value of P as well, value of holes as well. Because in the n-type semiconductor, it's not that only electrons will be there, holes will also be there, no? Holes will also be there. So P is equals to NV e to the power minus EV minus, not EV, EFN minus EV by KT. Say yes or no? Do you agree to this formula? P is equals to NV e to the power, here positive value I need to write down, but here the Fermi energy level we are putting as EFN. So if you solve it, what you are getting? EFN minus EV, that would be equals to KT ln NV by KT ln NV by P. So let's just say in the examination, they are talking about n-type semiconductor, okay? What they are talking about? They are talking about n-type semiconductor, and in the question they have mentioned the effective density of valence band. Then this formula you will apply. If effective density of conduction band is available, then this formula you will apply. This value you can find out on your own by using the mass action law. So what did you understand? That sir, this value is coming out to be KT ln NC by N, and sir, this value is coming out to be KT ln NC by P. Do you need to remember any of the formula? No. Not a single formula you need to remember. Okay? No formula you need to remember. It will not be used to find out anything. So don't worry about that. Are you able to understand this point? This is just these formulas are given in the textbook. That's why I wrote it down. Let's just say in the worst case in the examination they are saying that which of the formula is correct. Then can you derive it in one step only? You know that what will be the number of electrons? What will be the number of holes? In n-type, the number of electrons are more than the number of holes. That's why we focus on number of electrons. So in the examination, 99% chances are there that they will give the conduction band effective density of states. They will give the effective density of states for the conduction band. 99% chances are there. Okay. But in the worst case, for the n-type semiconductor, if they are giving the effective density of the states for the valence band, then you can apply this formula. Do you need to remember any of the formula? No. Okay, because we can derive it within the seconds. Let's just say NC value is given and number of electrons you already know. Then can you find out this value? Yes. So rather than applying this formula, I will apply this formula there. NC value I will put, N value I will put, then I can do the calculation. So no formula you need to remember. All good? Okay, fine. So in n-type semiconductor, the electron concentration N is much greater than the hole concentration P. So N is greater than P. Because of this, energy gap between the conduction band and the Fermi level is much smaller than the gap between the valence band and the Fermi level. Consequently, the Fermi level in n-type semiconductor lies closer to the conduction band than the valence band. So what they are saying, the energy gap between conduction band and the Fermi level is much smaller than the gap between valence band and the Fermi level. So this gap will be more and this gap will be lesser. And why this gap will be more? Because P value will be less, no? If I am saying that NC and V are same, if P value is less in n-type semiconductor, P value is less, that means this overall value is more, that means this overall value is more, that means this overall value is more. So the gap between EFN and EV will be more and the gap between EC and EFN will be lesser, because this value is more. If this value is more, then this total value is less, then this value is less, then this whole value is less. So gap between EC and EFN will be lesser. So the conduction band will, the Fermi level will be near to the conduction band and far away from the valence band. The thing that we did on the second page here, this thing I am proving for any random temperature now. Any random temperature, for any random temperature you can see the condition. Okay, I don't need to draw the diagram here because previously I have already drawn. So formula, do you need to mug it up? No, don't mug up the formula. You can derive it any day, but yeah, just remember this particular thing. Let's go to the p-type semiconductor. No, first I need to see the position of Fermi level in n-type semiconductor relative to the intrinsic Fermi level. What does that mean? That means that previously you were having your semiconductor. It was intrinsic. It was intrinsic. When it was intrinsic, at that time this was your Fermi energy level, right in between, right in the middle. Now when it became n-type, that means you started doping it, then it became n-type, then your Fermi level reached here. So how much this Fermi level has moved to EFN. Previously it was EFI, then it has moved to EFN. So how much it moved? This is what we are calculating. So in the examination, sometimes what they can ask, find out the energy gap between the Fermi energy level of n-type semiconductor to the intrinsic Fermi level. So basically this gap we need to find out. When it was intrinsic, this was your Fermi energy level. When it became extrinsic, when it became n-type, then this is the scenario. So what is the gap between EFN and EFI? So that we need to find out, but we will find it out after a break because I have been recording for a very long time. I need to take a break now. Okay, so we will find it out after a break. You can try doing it on your own. Which formula you need to apply? Think about it. 4 formula we are having. These 4 formulas we are having. Mostly more important are these 2 only. But yeah, think about it. Which formula will you apply and get the answer? Okay, let me take a break and then I will come back. Yeah, so did you try finding out the expression? So what we will do for n-type semiconductor, what is the number of electrons for n-type semiconductor? What could be my number of electrons? That would be equals to Nc e to the power minus Ec minus, here what I will write down, EFN, because I am talking about n-type semiconductor. So EFN by KT. Basically in my answer I need to introduce EFN and EFI. My target is to find out the difference between EFN minus EFI. This is my target. How can I introduce EFI? By talking about intrinsic semiconductor, right? For intrinsic semiconductor, what will be the scenario? In intrinsic semiconductor, number of electrons is equals to number of holes, that is equals to Ni. But I will be talking about number of electrons only. So here I will not put N because people will be getting confused. This N is this N is equals to Ni. But this N is of n-type semiconductor and this N is of intrinsic semiconductor. So when it was intrinsic semiconductor, when my semiconductor was intrinsic, at that time where was my Fermi level? At that time what was the number of electrons? This is a different case, and when it became n-type, then what was the number of electrons? This is a different case, right? So Ni is equals to Nc e to the power minus Ec. Here what I will write down? EFI by KT. Okay. So if I divide equation 1 with 2, what I will be getting? So you can do the division, or shall I do it? I guess you can do everything on your own now. You are getting N by Ni. That would be equals to e to the power minus Ec will be getting out. So basically you will see EFN minus EFI by KT. This is what you will be getting. Okay, N by Ni is equals to whatever it is, you don't need to remember it. Then what the final answer we are getting? EFN minus EFI is equals to KT ln N by Ni. So this answer you will remember. Okay. So again, one more thing I am asking you to remember, EFN minus EFI. If I am asking you to remember something, then I will surely tell you a trick. So what will be the trick? This gap I need to tell. Right? This gap I need to tell. With respect to the conduction band, which quantity is associated? Effective density of states. Effective density of states for the conduction band. Effective density of states for the valence band. Right? Here EFN EFN means I am talking about n-type semiconductor. In n-type semiconductor, who is the majority? Number of electrons. And when I talk about intrinsic semiconductor, so there who is the majority? Majority, minority, both are the same, and that is equals to Ni. So with EC, NC is associated, with EV, NV is associated, with EFN, N is associated, and with EFI, Ni is associated. Okay, so these are the associations. What formula I need to write down? I need to write down the formula between EFN and EFI. Difference between EFN minus EFI. That would be equals to, sir, KT would come, Ln would come. Now the problem would be that, sir, on upward side should I write N or Ni? Because with EFN who is associated? N. With EFI who is associated? Ni. So N by Ni would come or Ni by N would come. Now you know that value of N will be greater than Ni. What I know, N will be greater than Ni. And I know that this difference will be positive because EFN will be at higher level. So what will be the answer? N by Ni. There you go. Did you understand what I did here? EFN minus EFI. I need to remember KT Ln would come. Because how do I remember? Formula of, what was the formula of EFI? EC plus mid gap minus KT by 2 Ln. So KT Ln I can remember. Minus KT by 2 Ln NC by NV. So KT Ln I can remember. So sir, KT Ln would come. Now with EFN, N is associated. With EFI, Ni is associated. So KT Ln N by Ni. Right? This is how I can find it out. So this formula only I am asking you to remember. These formula that we derived here, these you don't need to remember. You will simply solve by this equation. This equation you are already remembering. But what may happen is that sometimes they can ask the difference between EFN and EFI. So either you derive in this manner or you just remember it. I have told you the way to remember as well. So only whichever that are necessary, those only I will ask you to remember. So here you can write down remember. Remember. But this you don't need to remember. These all things you don't need to remember. Okay. So KT Ln N by Ni. So similarly, all kind of formula will be there for the p-type semiconductor as well. In p-type semiconductor, where will be your where will be your Fermi energy level? Your Fermi energy level will be near to the valence band, right? So for p-type semiconductor, number of holes are given as total density of the effective density of the states for valence band, effective density of the states for valence band, multiply with probability of finding a hole in the valence band. Probability of finding a hole in the valence band, that is equals to e to the power, sir, minus here some positive value will come. So EFP is at the higher level than EV. So EFP minus EV by KT. So what will be the answer you will be getting? EFP minus EV. This you can do on your own. KT Ln NV by P. This is the answer you will be getting. Similarly, the same formula you can derive with respect to EC as well. What I mean to say is that N will be equals to NC e to the power, some positive value would come. So sir, EC is at the higher level than EFP. I am talking about p-type semiconductor. That's why I am putting down EFP. So from here, what will be the value of EC minus EFP? That would come out to be KT Ln NC by N. But rarely these formulas will be used, so you don't need to remember these formulas. Which formula you need to remember? You need to remember the formula of difference between these two guys. Difference between the intrinsic Fermi level and the p-type semiconductor and the p-type Fermi level. Intrinsic Fermi level and p-type Fermi level. What will be the formula? What do you think? Which is the quantity associated with EFI? That is Ni. And which is the quantity that is associated with EFP? That means p-type semiconductor. In p-type semiconductor, who are the majority? Holes are the majority. And one thing I know that P will be greater than Ni. So what do you think? What should be the formula? KT Ln. I am writing down the formula of EFI minus EFP. Now who is at the higher level? EFI is at the higher level. That means EFI minus EFP will be positive. So KT Ln higher value divided by the lower value. So KT Ln, which value will be higher? Number of holes will be higher. So EFI minus EFP. You can derive it with this derivation as well, but directly I have written the formula. How did I write it down formula? How did I write it down this formula? That also is clear to you. Okay. How did I derive it? what I will do, this P expression I will write down NV e to the power minus EFN minus EV divided by KT, and then NI expression I will write down NV e to the power minus EFI minus EV by KT, right? So from there I will divide and both of them, then I will get this formula. Only thing you need to remember this formula, and how will you remember that also I have told. That also I have told. How will you remember? Sir, KT ln, I know that the gap will be positive because EFI will be at the higher level. So higher concentration divided by the lower concentration, because P value will be greater than Ni. All good? So this is the formula that we need to see. So as of now, which all formula you need to revise? These formula you need to remember. Not too much formula. Okay, this formula you need to remember. Then nothing here you need to remember. Then this formula you need to remember. Okay. Then nothing here you need to remember. Then this formula you need to remember. Okay. And this formula you need to remember. Not much stress, right? Not stress at all. Sir, if I don't need to remember these formula, then why did you derive it? That means in the examination or in some notes or in some textbook, if you find out these formula written, then at least you should know that what is happening. Like, have we ever studied this formula? Yes, we have studied those formulas. If any day in the further lecture I use this formula to explain some other concept, because I will be explaining the concept of quasi-Fermi level. So there I will use this formula again. Okay. So there I will tell you that we derived those formula just for the understanding purpose. So in the examination for solving the problems it will not be used. For understanding a particular concept it will be used. That's why we are deriving it here. Okay. Now we have studied Ni square equals to A naught T to the power 3 e to the power minus Eg by Kt. And I told you I will give you the derivation of it. So let's see the derivation. Okay. So what is the value of N for intrinsic semiconductor? This is the concentration of a intrinsic semiconductor. So this is your intrinsic carrier concentration. So for intrinsic semiconductor, you know that N will be equals to, forget about intrinsic semiconductor, for any semiconductor, for any kind of a semiconductor, what do you know? For any kind of semiconductor, mass action law will be valid under thermal equilibrium. Mass action law will be valid under thermal equilibrium. So number of electrons will be equals to number of electrons multiplied with number of holes will be equals to Ni square. So N into P is equals to Ni square, that I know, right? So what I am putting, again I am putting N into P equals to Ni square. What is the number of electrons? What is the formula of number of electrons? Number of electrons will be density of states multiplied with e to the power, or something positive would come here. So EC minus EF by KT, right? EC minus EF. EF will be in between. So EC minus EF divided by KT. And what about P? So P will be NV e to the power, positive value would come. So who will be at the higher level? EF or EV? EF will be at the higher level. So EF minus EV by KT is equals to Ni square. What is NC? You know NC is equals to NC naught Mn star T to the power 3 by 2, and NV is equals to NV naught MP star T to the power 3 by 2. So here we need to see the variation with respect to temperature and band gap. We need to see the variation with respect to temperature and band gap. So I don't need this value. I don't need Mn star. So Mn star and MP star I will take as a constant, because they will be constant value only, no? Effective mass, that will be constant. I just need to see the variation of Ni square with respect to temperature and band gap. So that I am seeing. So I will put the value here. NC naught Mn star to the power 3 by 2 and T to the power 3 by 2, and this value also I am putting now. NV naught MP star to the power 3 by 2 T to the power 3 by 2 e to the power minus EC plus EF minus EC plus EF minus EF plus EV divided by KT. So this and this is getting cancelled out. EV minus EC, or you can write down minus of EC minus EV. So what will be your EC minus EV? This is your EC and this is your EV. So what will be your EC minus EV? Band gap. So here what you are getting, e to the power minus EC plus EF minus EF. So EF is getting cancelled. EV minus EC you are getting. So EV minus EC will be equals to EV minus EC will be equals to minus Eg. So here you are getting e to the power minus Eg by kT, minus Eg by kT. That is coming out to be equals to Ni square. So now you see constant, constant, constant. Why constant? Because we are seeing the variation with respect to temperature, and this is also constant. So all constant multiply A naught. So first I am writing down this Ni square. So Ni square. One more thing I would like to tell here is that let's not put these values. What I would do is that let's take it downward, and before that I want to include one more step. Nc multiply with Nc multiply with Nv. So Ni square is equals to Nc multiply with Nv, and then you know that e to the power minus Ec plus Ef, whatever it would come, then you would know that it will be replaced with minus Eg by kT. So this formula you don't need to mug up. If you can remember, then you can remember. Okay, if you can remember, then you can remember. Otherwise, you can derive it any day, because what may happen is that in the examination, what they can give you the Nc value, they can give you the Nv value, and they can give you the Ni square value. They can ask you the band gap, or they can give you Nc, Nv band gap value. They can ask you the Ni square value. Are you able to understand this point? So this formula is also used in one of the question. Not in the examination till this date. Not in the examination this question have been asked, but in Niemann, this formula is given and it has been used in one of the numerical as well. So it can be asked in your examination. So Ni square equals to Nc Nv e to the power minus Eg by kT. If you are able to remember, then remember. Otherwise, you can derive it any day. N into P is equals to Ni square Nc e to the power minus Ec minus Ef by kT into Nv e to the power minus Ef minus Ev by kT. So very simple derivation. Nc into Nv e to the power minus Eg by kT. From there, we got the same thing, and from here we understood that Ni square is equals to some constant t to the power 3 by 2 t to the power 3 by 2. That will become t to the power 3 e to the power minus Eg by kT. So this formula that we have understood, that we have written here. So Ni square equals to a naught t to the power 3 e to the power minus Eg by 2 minus Eg by kT. Just the derivation, no one will ask you. If you remember it, then it is good. Otherwise, try remembering this one. So I am just putting a word R here, Re. Try remembering this one if you can remember. So shall we just write down that what all things we need to remember? After that, we need to solve the questions only. So let's write down as a summary, formula summary, that what all things you need to remember. Formula to remember. If you just remember this slide, then your job will be done. Probability of finding the electron at a particular energy level E, that is given by 1 upon 1 plus e to the power E minus Ef by kT, and that would be given as e to the power minus E minus Ef by kT. Then directly number of electrons. Number of electrons will be Nc e to the power something positive would come, sir. So Ec minus Ef by kT. Then number of holes, sir, Nv e to the power something positive would come, that means Ef minus Ev by kT. This formula. Then what will be the value of Fermi level in intrinsic semiconductor? That would be equals to mid gap Ec plus Ev by 2 minus kT by 2 ln Nc by Nv. Okay. Secondly, Nc is equals to Nc naught Mn star t to the power 3 by 2, and Nv is equals to Nv naught Mp star t to the power 3 by 2. Done? Okay. Then who will be at the higher level? EFN will be at the higher level. EFN minus EFI. What that would be? EFN minus EFI. So you will draw the diagram. Then, sir, KT ln N will be greater than Ni. So N divided by Ni. Second, sir, EFP, not EFP, EFI minus EFP. Why so? Because EFI will be at the higher level. So KT ln P by Ni. And lastly, sir, Ni square is equals to Nc into Nv e to the power minus Eg by kT. Nc into Nv e to the power Eg minus kT. There you go. These are the formula. That's it. Just if you remember these formulas, your job will be done. So 1, 2, 3, 4, 5, 6, 7 and 8. All with respect to all these formula, like a lot of questions you will be able to solve. Let's get started with this particular question. Silicon at a temperature of 300 Kelvin has its Fermi level positioned 0.25 below the conduction band. Okay, 0.25 electron volt below the conduction band. The effective density of states in the conduction band is given. NC value is given 2.8 into 10 to the power 19 centimeter cube, and it is below the conduction band. That means EC minus EF is given. The Fermi energy level, Fermi level is positioned 0.25 electron volt below the conduction band. So this is the conduction band and this is my Fermi level. Conduction band and this is my Fermi level. So that is 0.25 electron volt. Calculate the probability that a state in the conduction band is occupied by an electron. So what you need to find out? Probability of finding an electron in the conduction band. That would be equals to 1 upon 1 plus e to the power EC minus EF by kT, and I know that sir it will be approximately equals to e to the power minus EC minus EF by kT. Every calculation is going at 300 Kelvin. 0.25, 0.0259. So very simple thing, everything you already know. So let me do this calculation. Yeah, so answer you are getting is 6.43 into 10 to the power 5. Okay. Next, calculate the thermal equilibrium electron concentration in silicon at 300 Kelvin. So this was A, this was B. Thermal equilibrium electron concentration at silicon at 300 Kelvin. So what will be the number of electrons? So number of electrons will be Nc e to the power minus EC minus EF by kT. Number of electrons will be Nc multiplied with the probability of finding an electron in the conduction band. So Nc into e to the power minus EC minus EF by kT. So Nc value is 2.8 into 10 to the power minus 19. Not minus 19, sorry, plus 19. And this probability is 6.43 into 10 to the power minus 5. So 6.43 into 2.8. So 1.8. So 1.8 into 10 to the power 15. 1.8 into 10 to the power minus 4. Minus 4 with minus 19. Yeah, 10 to the power 15. Yeah. So this is the answer you will be getting. Centimeter cube inverse. Very simple calculation. Very straightforward. Like there is nearly nothing in these kind of problems. Okay. So rather than mugging up the formula, we remember the concept and we will remember our tricks as well. Silicon at 400 Kelvin. Always notice the temperature. Whenever you solve a question of EDC, always notice the temperature. Silicon at 400 Kelvin has its Fermi level positioned 0.27 electron volt above the valence band. So what is given? Fermi level minus valence band is 0.27 electron volt. Everything is running at 400 Kelvin. The effective density of the states for the silicon at 300 Kelvin is given as 1.04 into 10 to the power 19. So NV value at 300 Kelvin is given as 1.04 into 10 to the power 19. What I need to find? Calculate the thermal equilibrium hole concentration. So what I will do? Sir, this is what I need to find at 400 Kelvin. You need to find everything you need to find at 400 Kelvin. So sir, it would be EV e to the power something positive should come. So sir, for the positive EF minus EV by kT. Now all these calculation you need to do at 400 Kelvin. So what all things will change with respect to the temperature? NV value will change and this kT value will also change, you know. Thermal energy will also change. NV is NV is proportional to temperature to the power 3 by 2. So NV value at 400 Kelvin will be divided by NV value at 300 Kelvin will be equals to 400 divided by 300 to the power 3 by 2. So what will be the NV value at 400 Kelvin? that would be 4 by 3 to the power 3 by 2 multiply with 1.04, right? 4 by 3 to the power 1.5 multiply with point so 1.6 into 10 to the power 19 centimeter cube inverse. Did you understand this point? NV is proportional to T to the power 3 by 2. Then you did the same thing. 4 by 3 to the power 3 by 2. So 4 by 3 to the power 3 by 2. What that would be? 4 by 3 to the power 3 by 2. So whatever the value it is, multiply with NV value at 300 Kelvin. So that is 1.04. So this is the answer I am getting. What about the VT value? Or you can say thermal energy value. So this is also proportional to temperature. What I mean to say is that thermal energy, here I can simply do the calculation. So your thermal energy is also proportional to temperature. So your thermal energy at 400 Kelvin yeah, so your thermal energy at 400 Kelvin divided by your thermal energy at 300 Kelvin is equals to temperature. Temperature is 400 divided by 300. So what will be the answer of thermal energy at 400 Kelvin? That would be 4 by 3 into 0.0259, right? 4 by 3 times of 0.0259 into 4 by 3, 0.034. So this is the scenario, electron volt. Okay. What is the value of NV? NV is 1.6 into 10 to the power 19 e to the power minus EF minus EV. EF minus EV is 0.27. So this value is already given at 400 Kelvin only, right? Divided by KT, that is 0.034. So from here I will get the answer. 0.034 reciprocal 0.27 plus minus e to the power into 1.6. So yeah, 6.43 into 10 to the power 15. So question was very simple only, just like the previous problem only. Whatever that we did in the previous problem, the same thing we are doing here. Just the thing is, with respect to temperature, things are changing. So with respect to temperature, NV value is also changing and ET value is also changing. Well and good. A germanium arsenide at 300 Kelvin has effective density of states in the conduction band as Nc and valence band this much. I'm really sorry for this particular thing, right? I hope you guys are not getting irritated. I know it might be sometimes it might be problem that your educator is not speaking fluently or clearly. I'm speaking fluently, I'm speaking clearly as well, but there is some break because of this thing, right? Because of my throat. And I was eating some elaichi and all these things. Don't think that I am a fan of Ajay Devgan. Okay, I am not eating गुटखा वगैरह नहीं खाता हूँ मैं. इलायची वगैरह खा के मैं रिकॉर्ड करता हूँ ताकि कम खांसी आए. ठीक है, तो ये थोड़ी सी दिक्कत हो रही है, बट मैं इसको डिले नहीं कर सकता क्योंकि फिर सिलेबस बहुत लेट हो जाएगा. तो आई नीड टू कवर द सिलेबस एज वेल. सो I hope it is not being that much of a problem for you guys. Okay, so you guys need to cooperate, and you can put a like if you are watching it on YouTube. You can put a like. Yeah. Band gap is given, NCNV value is given, and band gap is not changing with respect to the temperature. You need to find the intrinsic carrier concentration of gallium arsenide at 450 Kelvin. So try doing it on your own. What is the formula that we saw? NCNV e to the power minus Eg by KT. Now they are saying that this Eg is constant. This is not changing with respect to temperature. Rest all the things will change with respect to the temperature. This will change, and this will also change. So what will be your NC value at 450 Kelvin? So sir, that would be equals to 450 divided by 300, the value at 300. What is the value? 4.7 into 10 to the power 17. But it is proportional as power 3 by 2. Is that clear to you? NC value at 450 divided by 300 to the power 3 by 2 into 4.7 into 10 to the power 17. So what we are getting? 4.5 divided by 3 to the power 1.5 into 4.7, so 8.63. And what about NV at 450? So that will also go through the same thing. So 1.5 to the power 1.5 into 7. So 12.85 into 10 to the power 18 centimeter cube inverse. Now what about the ET value? ET value at 450 Kelvin. So that would be 450 divided by 300 into 0.0259. So 450 divided by 300 into 0.0259. 0.3885 electron. There you go. Now you can solve it. So Ni square is equals to 8.63 into 10 to the power 17, 8.63 into 10 to the power 17 into 12.85 into 10 to the power 18 e to the power minus, Eg is not changing with respect to the temperature, they are saying, but actually it changes, but they are saying that band gap is not changing with respect to the temperature. So 1.42 divided by kT, that is 0.03885. So this is the scenario, this will be the answer. So there we go, 1.42, 1.42 divided by 0.03885 plus minus e to the power. So 1.33 e to the power minus 16 I am getting. So 8.63 I will write down here, 12.85 I will write down here, 10 to the power 17, 10 to the power 18 into 1.34 10 to the power minus 16 I am getting. So effectively 10 to the power 19 I have. So 10 to the power 19 I have, and rest all the values I will multiply. Multiply with 8.63, multiply with 12.85. So the whole result they are giving me in 10 to the power minus 14. So whole result I am getting 1.48 into 10 to the power minus 14 into 10 to the power 17 into 10 to the power 18. This is what I am getting. So what I can see here, 10 to the power 3, so 10 to the power 21. So 1.48 into 10 to the power 21 Ni square. Now how will you do the calculation? Here try making something that is even 10 to the power 20, because you know that I will be able to take the under root. What I would do is that I will write this down as 14.8 into 10 to the power 20. Right? I took the 10 outside it, 14.8 into 10 to the power 20. Now Ni value will be under root 14.8, right, into 10 to the power 10. Say yes or no? Because under root of 10 to the power 20 will be 10 to the power 10. So now I just need to calculate 14.8 under root, that is coming out to be 3.84. Yes. So Ni value is coming out to be 3.84 into 10 to the power 10 centimeter cube inverse. So this is how you do the calculation when it comes to EDC. So that's why I am showing you every step. Are you able to understand this point? Because in EDC calculation takes a very important role. These are, none of them are PYQ, okay? None of them are PYQ. You will be able to solve the PYQ very easily. In PYQ, you will not find that this much temperature is changing. Very straightforward question would be there. These questions I am taking from Neiman only. Although written by ChatGPT, but taken from Neiman. Here, what did I tell you? That effective mass of electron should be greater than the effective mass of holes. But here, things are different. So if things are different, there you will not be say, sir, it will be MTA. No. Whatever the value is given, I need to solve it. That's it. What they are asking? In silicon, effective masses are given as this much. Calculate the position of intrinsic Fermi level with respect to the center of the band gap. Center of the band gap. So Fermi energy level is equals to EC plus EV by 2 minus kT by 2 ln Nc by Nv, and I know that Nc is proportional to Mn star to the power 3 by 2 and Nv is proportional to Mp star to the power 3 by 2. So what I can see, EFI minus E mid gap is equals to minus kT ln Mn star to the power 3 by 2 and Mp star to the power 3 by 2, already to the power 3 by 2. So this 3 by 2 can go in front. So what will become 3 by 4? So minus 3 kT by 4. Now you can put the value at 300 Kelvin. Yes. So minus 3 into 0.0259 divided by 4 ln Mn star is 1.08 divided by 0.56. So 1.08 divided by 0.56 ln into 3 by 4 into 0.0259. So 0.0127. 0.0127 electron volt, and minus sign is already there. So EFI minus E mid gap. This is what you are getting, or you can write down EFI minus E mid gap is actually coming out to be minus 12.7 milli electron volt. What does that mean? That means your intrinsic Fermi level is 12.7 milli electron volt below the, what they are asking, position they are asking. So it is below the intrinsic Fermi, below the center of the band gap. Your Fermi energy level, your intrinsic Fermi level is 12.7 milli electron volt below the center of band gap in silicon. Okay. So EFI is 12.8. I will write down 12.7 below center of mid gap. Is below from the center of mid gap. Okay, from center of mid gap it is 12.7 milli electron volt below. This is the answer. Let's go to the next one. Consider silicon at this much temperature. Effective density of states in the conduction band is given. Effective density of states in the valence band is given. The Fermi level is located 0.25 electron volt below the conduction band H. The band gap in the silicon is 1.12 electron volt. Okay. So let's make the diagram. EC, EV, and Fermi energy level is 0.25 electron volt below. So this gap is 0.25 electron volt. And what is this total gap? What is this total gap? This total gap is 1.12 electron volt. So what do you think? What is this gap? 1.12 minus 0.25. 0.87, right? Now what you need to find? Thermal equilibrium, electron and hole concentration, right? So electron concentration will be equals to Nc e to the power minus Ec minus Ef by kT at 300 Kelvin only. No, temperature is not even mentioned. Oh, mentioned. Yeah. So that would be equals to, what is the value of Nc? 2.8 into 10 to the power 19 e to the power 0.25, 0.0259 So 0.25 divided by 0.0259 into 2.8. So 1.8 into 10 to the power 15. Yeah, 1.8 into 10 to the power 15 centimeter cube inverse. What will be the number of holes? E to the power minus EF minus EV by KT, right? That is 1.04 into 10 to the power 19 e to the power minus EF minus EV. EF minus EV is 0.87 divided by 0.0259. So 0.87 divided by 0.0259 plus minus e to the power into 1.04. So 2.68 into 10 to the power 4. Yeah, so 2.7 into 10 to the power 4 centimeter cube. Very simple question. Okay. And you ask these questions to your friends who are studying from somewhere else. They will not be able to solve very easily. They will see, okay, sir, this formula was there, that formula was there. Sir, how will I relate with NC? Okay, this thing I will apply. So forget about the formula. N equals to NC this formula, P equals to NB this formula. That's it. Okay. So we are not mugging up any formula. Whatever the formula that we need to remember, we have written in one slide only. Okay. Silicon at 300 Kelvin contains a, yeah, this is a good question. You should try it on your own. I think this is the last one. Yeah. So silicon at 300 Kelvin is having impurity concentration of 10 to the power 16. And somewhere intrinsic carrier concentration is also mentioned, so that I have also put. Determine the concentration of donor impurity atoms that must be added. So you are adding Nd to make it n-type, such that it becomes n-type and the Fermi level is located 0.2 electron volt below the conduction edge. So that means this is the conduction band, this is the valence band. So as per you, your Fermi levels should be here. 0.20 electron volt. So you need to add up Nd, right? The effective density of states are given. Only for Nc the effective density of state is given. So for conduction band this is given. Now which formula do I know? The intrinsic carrier concentration is this. So how much Nd I need to dope? So which formula I know? I know the number of electrons. Number of electrons would be equals to Nc e to the power minus Ec minus Ef by Kt. So this thing I know. I know the value of Nc. Yes. Ec minus Ef also I know. Kt also I know. Basically, I will see what all things are given. Nc is given, Ec minus Ef is given. So I can find out the number of electrons. So total number of electrons will be this much. So what is the value of Nc? E to the power minus, what is Ec minus Ef? 0.20 divided by 0.0259. So 0.2 divided by 0.0259 plus minus e to the power into 2.8. So 1.24 into 10 to the power minus 3. So what we are getting? 1.24 into 10 to the power minus 3. 1.24 into 10 to the power minus 3. Or better write down 12.40. I will write down 12.40 into 10 to the power minus 4. So it would be 12.40 10 to the power 15 centimeter cube inverse. These are the number of electrons that you are getting. This is what? This is the number of electrons. Now what do you know? What kind of semiconductor it is? N-type or compensated N-type? This is your compensated N-type. So for compensated N-type semiconductor, number of electron is equals to Na minus Nd by 2 plus under root Na minus Nd by 2 whole square plus Ni square. Now you know that Ni will be much lesser than Na minus Nd, because you know that already Na is very higher, Nd will be higher than that, so you are nowhere considering Ni, so this will go to 0. So you know that N value will be approximately equals to Na minus Nd. So from here, array yaar, compensated N type it is, so Nd minus Na, sorry guys, Nd minus Na, Nd minus Na, Nd minus Na. So N will be Nd minus Na. So what will be the value of Nd? Nd will be N plus Na. So you can see 12.40 into 10. So 1.24 10 to the power 16 was a better option. 1.24 into 10 to the power 16. So 1.24 plus 1.24 10 to the power 16 plus 10 to the power 16. What that would be? 2.24 10 to the power 16 centimeter cube inverse. So this will be the value of Nd. That's the answer. Or better, I should keep this in the answer. All good? All fine? Very simple thing. Okay. Now the next topic is also very simple. Variation of Fermi level with respect to the temperature and doping concentration. So first we will see with respect to the doping concentration. So both in N type and P type we are going to see. So on y axis I am making energy, on x axis I am making doping concentration. That means if you are working on x axis, if you are moving on x axis, then your doping concentration increases. So for N type, and this is your conduction band, this is your valence band, and in between I am making intrinsic Fermi level. So initially you are having intrinsic semiconductor only, then you are doping it to make it N type. So for N type, what will be the scenario? For N type, I know that first we will see with respect to formula, then we will see with respect to concept as well. EC minus EFN. I don't remember the formula, but I remember this thing. What do I need? What do I remember? Number of electrons is equals to NC e to the power minus EC minus EFN by KT. So from here what I will get? KT ln N by NC. So what I will get? KT ln NC by N. This is what I will be getting. From this only I have written down this formula. Although I don't remember it, but how will I write down? From here I can write down EC minus EFN KT ln NC by N. Right? Now you know that if doping increases, then value of N will increase. The value of N will increase. And if the value of N will increase, then this value will decrease. Then this value will decrease. So the gap between EC and EFN will decrease. EC and EFN will decrease. That means if you are doping more, then you are going towards a conduction band. So let's just say at a particular doping, you are here, and if you are moving in the x-axis, that means you are increasing the doping concentration. So as you increase the doping concentration, what happens? You move near to the conduction band. So this is your EFN. As you increase the doping concentration, basically previously what was the scenario? It was intrinsic. Just as I started doping it more, just as I started that donor concentration, just I started putting the donor concentration, what really happened? This started moving upward. So if I put more and more donor concentration, this will move more and more upward. So this is what I am doing. I am drawing it with respect to energy versus doping concentration. Energy versus doping concentration. So if doping concentration is more, if your doping concentration is more, that means you are more near to EC. Are you able to understand this point? Now let's just think about a semiconductor. Now this analysis is only important, otherwise you will be getting confused. Forget about it. Whatever that I told you till this point, you understand in this manner only. More doping, more near to EC. Lesser doping, further away from EC. But if it is N type, then surely you know that it will be greater than EFI. That you already know. If it is N type, then surely you know that it is greater than EFI. So more doping means more near to EC. That means here I am putting more doping. Okay. And similarly for P type, what you will do? For P type, what will be the formula? EFP minus EC, right? EFP minus EC, that would be equals to KT ln NV by P, KT ln NV by P. So more doping means these will increase, because more, if you are putting more trivalent atom, then more number of holes will be there, so this will increase, and if this is increasing, then this is decreasing, then this is increasing. That means more doping means EFP minus EC will decrease. That means EC will come near to EFP. So lesser doping means it was here, and more doping means it is coming near to valence band. So initially it was intrinsic. Then what you did, you started doping the acceptor atom. So acceptor atom you started doping. So Fermi level started moving downward, 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 and when the doping was maximum, it has moved here. So this is about your EFP. So this is here as well, more doping. Very simple thing, very, very straightforward. Just remember that this is energy versus doping concentration. This is not energy versus X. Here we were drawing this diagram. All these diagrams are energy versus distance. Energy versus distance. So with respect to the distance, they are flat only. What I mean to say is that, do you remember the first lecture? In the first lecture, what we did? Let's come here. In the first lecture, what we did? 3s, 3p, 3s, 3p. Then this kind of diagram we got, right? This kind of diagram we got. This I called as conduction band, and this I called as valence band. So here what we were doing, we were going with respect to distance only. No, this was energy, this was distance. So as I was reducing the distance, this is what I got. So here I made the conduction band, here I made the valence band, and here I made the conduction band. So those I made with respect to the distance. So these conduction band and valence band that we draw, these we draw with respect to the distance. Are you able to understand this point? Now what I am doing, energy versus doping concentration. So based on the doping concentration, EC and EV will not change. EFI will also not change. Who will change? Based on the doping concentration, these EFN and EFP will change. So always look at the x-axis. What x-axis is given? Energy versus X would be different. Energy versus doping concentration would be different. Are you able to understand this point? As the doping concentration increases, the gap between the conduction band and the Fermi energy level of N type will decrease. As the doping concentration increases, the gap between the valence band and the Fermi level of P type will also decrease. That's it. Okay, more doping means more near to your conduction band or valence band. All good. So this is what has been written. In N type, higher donor doping brings Fermi level closer to the conduction band and farther from the intrinsic level. In P type, higher acceptor doping brings the Fermi level closer to the valence band and farther from the intrinsic level. Very simple thing. Next, this is the question. So this is like part A and this is part B. Two questions are there. Which semiconductor has more doping and what is the nature of doping? So in both of the semiconductor, donor atoms are doped, right? Donor doping. Why so? Because near to the conduction band, farther from the valence band, and here near to the valence band and farther from the conduction band. So here also, here acceptor doping. Very simple question. Free marks if these kind of questions are coming. Now, which semiconductor is having more doping? Between semiconductor 1 and semiconductor 2, which is having more doping? Semiconductor 2. Why so? Because in the semiconductor 2, the conduction band and the gap between the conduction band and the Fermi level is very low. More doping means you are moving more towards the conduction band. So here more doping is there. That means ND2 is greater than ND1. And what about this one? Na2 is greater than Na1. Why so? Because you are more near to the valence band. So if you are more near to the valence band, what does that mean? That means acceptor atoms are more here. So if acceptor atoms are more, that means your Fermi level will be near to the valence band. Very simple thing. Okay, very straightforward. Let's draw with respect to the temperature. So now I will have to vary the temperature. So again for N type I will write down the formula. Which formula I will write down? Sir, EC minus EFN. Although sir you don't remember the formula, so no need to remember the formula. KT ln, you can any day you can derive it. KT ln NC by N, right? Yes. Now if temperature increases, then the gap between EC and EFN will increase. If the temperature increases, if I go on this axis, if I move towards a temperature axis, then the gap between EC and EFN will increase. This is your EC, this is your EV. Let's just say I started my EFN from here, so gap will keep on increasing. The gap will keep on increasing. So this is your EFN. Similarly for P type, EFP minus EV, that would be KT ln NV by P, right? So as you increase the temperature, the gap between Fermi energy level and the valence band will increase. So as I increase the temperature, the gap will keep on increasing. So this will be your EFP. So here there is more temperature. Here there is more temperature. Very simple thing. And do you remember the graph of number of electrons with respect to the temperature? Increases, 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 and then at a very high temperature it is becoming intrinsic. That means if you are increasing the temperature, that means you are going towards making your semiconductor as intrinsic semiconductor. So if I am increasing the temperature, my Fermi energy level for both N type and for P type, for both of them it is moving towards intrinsic Fermi level. So as I increase the temperature, that means I am moving towards making my semiconductor into intrinsic semiconductor. That means my Fermi level will try to move towards intrinsic Fermi level. Or you can simply see from the formula, if temperature increases, the gap between EC and EFN increases, the gap between EC and EFN is increasing. Very simple thing, right? So this is what has been written. As temperature increases in N type, the gap between the conduction band and the Fermi level increases, while the gap between the Fermi level and intrinsic level decreases. But basically, this gap is decreasing and this gap is increasing. This is what it is saying, right? Initially, this gap was here. Initially, this gap was this much. Okay, well and good. So these are the diagram. This is the theory that has been written. And similarly for P-type semiconductor also, it has been written. Again, a very simple question. The same kind of simple question. You need to find out the relation between T1, T2. That means this is the relation. This is question A. This is question B. Energy versus the array R. Yeah, energy versus X. This graph was energy versus X, right? Energy versus X. And this graph was energy versus temperature. And this graph is also energy versus X. Are you able to understand this point? This is now with respect to the distance. Now only thing you need to know is that the gap between EC and EFN is reducing here. And here it is more. What does that mean? If the gap is more, that means more temperature. So T1 is greater than T2. And here if the gap is more, that means T3 is greater than T4. Because if the temperature is more, if temperature increases, this gap increases. Because formula says KT ln. Or you can say that if temperature increases, that means I am moving towards making my semiconductor into intrinsic semiconductor. So if temperature increases, I am actually moving towards intrinsic semiconductor or intrinsic Fermi level. So this temperature T3 will be greater than T4, T1 will be greater than T2. So always you need to look at the examination that what they are asking. They are asking the graph with respect to temperature or with respect to the distance. So with respect to the distance, we have seen the graph is EC, EV, EFI in that manner and EF. Only thing that can change is the gap. The gap. Rest all the things will be flat. This is what we are studying till this point. Energy versus X. Till this point we have seen the graphs are flat with respect to the distance. All whatever that can change is the gap, this gap, this gap and this gap. Okay. Well and good. Now this question will be interesting. Read the question and tell the answer. It is MSQ. Okay. It is MSQ. Read the question and tell the answer. For different doping concentration in both N-type and P-type semiconductor, the gap between the Fermi level and intrinsic Fermi level is shown. What is shown? EFP minus EI is shown and EFN minus EI is shown. Basically, if I make the diagram, this is my conduction band, this is my valence band and this will be my EFI. I know that this will be my EFN and this will be my EFP. So conduction, valence, EFI, EFN and EFP. So EF minus EFI versus the temperature is shown. What does that mean? As you increase the temperature, what you see? As you increase the temperature, the gap between EF and EFI is becoming lesser. Here this was the gap and then it is becoming lesser. So increasing the temperature means the gap between EF and EFI is becoming lesser. Here what is the gap between EF and EFI? Almost around 0.2, and then here the gap has become 0. Here what is the gap? Almost around 0.2, then it has become 0. Why it is for P type and why it is for N type? Because in P type EF minus EFI will be negative, because EFI will be at a higher level. And why it is for N type? Because in N type EF minus EFI will be positive. Is that clear to you? Although it is not answering our question, question will be answered based on the fact that which one will be larger, ND2 is greater than ND1 or NA1 is greater than NA2, whatever the relation is there, that we need to tell. Now I know that at a particular temperature, if there is more doping, what I am saying, at a particular temperature, I am fixing the temperature. I am fixing this temperature. This temperature is T. If there is more doping, what does that mean? That means this gap will be lower. More doping means EFN will be moving towards EC. That means this gap will be larger. So what I am saying, more doping shows that EFN minus EFI will be larger, and EFP, or you can say EFI minus EFP, will also be larger. Because if there is more doping, that means your EFP is moving towards valence band. That means this gap will increase. So at a particular temperature, I am only varying the doping, not temperature. So at a particular temperature, who is having more gap? This guy is having more gap or this guy is having more gap? ND2 is having more gap than ND1. So what will be the answer? And here who is having more gap? Na2 is having more than the Na1. More doping means there will be more gap between EFI and EFP, because EFP will be moving towards EV and EFN will be moving towards EC. That means there will be more gap between EFI and EFN as well. More doping. So who is having more gap? Here the gap is roughly around 0.2, but here the gap is roughly around 0.3. And in this case, here the gap is roughly around 0.2, but here the gap is roughly around 0.3. You can see this is a different axis. This is not 0 here. This is not 0 here. This is 0 here. So 0 and downward everything is negative. 0 upward everything is positive. So EF minus EFI versus temperature graph is given. In the examination, what may happen is that they can simply ask this graph, or based on the graph they can ask the question. And surely in 2026 or in 2027 the question is coming like this. Surely in your examination you will see very soon this kind of question is coming. This kind of graph they can directly ask, that EF minus EFI versus temperature graph, how it will go for N type and P type. So that you should be able to make. You are able to understand this graph, right? As the temperature increases, you are moving more towards a intrinsic semiconductor, or you can say you are increasing more towards a intrinsic Fermi level. That means this gap will keep on reducing. So yes, this gap is reducing. Why it is for N type, why it is for P type? Because in N type this gap will be positive, in P type this will be negative. So this is how the graph will go. And this graph is given in Niemann. From that particular graph I made this question. Okay. So surely it is coming very soon in your examination. So that's it about this topic. Is there anything else? No. Yeah, we can see this thing, degenerate and non-degenerate semiconductor. So some points we need to see, some discrete point we need to see, that is degenerate and non-degenerate semiconductor. Do you remember what was degenerate and what was non-degenerate? In degenerate I said that there will be more doping, and here there will be moderate doping. Moderate doping. Here what was the ratio? You don't need to remember it. 1:1 to the power 3, and here 1:1 to the power 7. Right? So if I am increasing the doping, then what is happening? If you increase the doping, then let's talk about N type semiconductor. If you increase the doping, what will happen? This EFN will move upward. So what if I do so much of doping that EFN is moving into EC? What I am saying, I have done so much of doping that my Fermi level has moved into conduction band. So if that scenario is happening, that means it is degenerate semiconductor, otherwise it is non-degenerate semiconductor. So we are studying all the cases about non-degenerate semiconductor, that we will not do so much of doping that our EFN will get into EC. our Fermi energy level will not get into EC. We will not do so much of doping. We will make sure that we do that much of doping only such that EC is always greater than EFN. That means our Fermi energy level is never getting into the conduction band. So this is something that has been written. Okay. Non-degenerate semiconductor doping is moderate. The Fermi energy level lies within the band gap. That means it will be closer to the conduction band and closer to the conduction band for N type and closer to the valence band for P type. The level will be lying between the band gap. That means this will be conduction band, this is the valence band, and this is known as band gap. So here you can find out, here you can find out, wherever you can find out. So the Fermi energy level will be lying inside the band gap. Okay. Carrier concentration is low enough to follow Boltzmann stats. Okay. What do you mean by Boltzmann statistics? That means f of E is approximately equals to e to the power minus E minus EF by kT. So this approximation is valid in our case. Okay, in our case this approximation will be valid, and in your examination as well this approximation will always be valid. Degenerate semiconductor doping is very high. Fermi level enters into the conduction band and over the valence band. Carrier concentration is so high that material will behave like almost like a metal, and Fermi direct statistics we need to use. What is Fermi direct statistics? F of A is equals to 1 upon 1 plus e to the power E minus EF by kT. That complete formula we need to use. All good. So in short, non-degenerate semiconductor means Fermi level inside the band gap, and degenerate semiconductor means Fermi level inside the band. Band could be conduction band or valence band. So if your Fermi level is entering into the conduction band or valence band, that means surely it is degenerate type of semiconductor. Otherwise it is non-degenerate type of semiconductor. Okay. Now in GATE 2024 there was a question. There was a term mentioned, degeneracy factor. What do you mean by degeneracy factor? So if I am saying that an energy level E1 is having degeneracy factor of 2. Energy level E1 is having degeneracy factor of 2. That means E1 is having two states. E1 is having two energy states. So degeneracy factor of energy level E1 is 2. That means energy level E1 has two energy states. If degeneracy factor is 5, that means it will have 5 energy states. If degeneracy factor is 10, then it will have 10 energy state. So on one level, on one floor, there are 2 rooms available. If I am saying that degeneracy factor is 2. Okay. So use your whole brain and solve this question. Don't apply any formula that you have studied. Let's just say you might have studied this EDC chapter from somewhere else. So they will solve this question with respect to some formula. They will write down some formula and they will solve it. I can also write down the formula. But if I write down the formula, then you will not be learning anything, right? You will just mug up the formula, and it is not possible to remember so much of formula in the examination hall. So minimum formula we are trying to remember. Minimum, least formula we are trying to remember, right? So you are not going to mug up any formula. Use your brain here. What this question is saying, make the diagram and try to get the answer. I am pretty sure you will be able to get the answer. I have also told the meaning of a degeneracy factor. That means on one energy level, there will be 2 states. So try thinking about it and try to get the answer. And if you are able to get this answer, then go for this particular question and tell me the answer for this particular question as well. Okay. So try solving this one and this one. And with that, this topic will end. Then we need to start this particular topic, energy band diagram for different kind of semiconductors. So this is also a very interesting topic, but first we need to solve this question and this question. So you try solving it on your own. I will have to drink some water and then I will come back and let's see. We will try solving these problems. Okay. Yeah, welcome back. So did you attempt this question? A non-degenerate N-type semiconductor is having 5% neutral dopant atoms. Fermi level is located 0.25 electron volt below the conduction band. So basically, we know one thing now, that this will be our conduction band. This is our Fermi level. So EC minus EF is given. That is given by 0.25. This distance is given 0.25 electron volt. And donor level ED is having a degeneracy of 2. What does that mean? That means if this is my donor level, ED, on this donor level there are two rooms, that means there are two states. Okay, this is the meaning of degeneracy of 2. Degeneracy factor is 2. So there are basically two states. On one donor level there are two donor states. This is the meaning of degeneracy of factor of 2. Thermal voltage you need to take 20 millivolt. Thermal voltage you need to take 20 millivolt, although it is 26 millivolt, but 20 millivolt you need to take. You need to find out the difference between EC and ED. So basically you need to find out EC minus ED. This is our target. Okay. What is the meaning of a semiconductor having 5% neutral dopant? What does that mean? That means let's just say this was my intrinsic semiconductor. Here I did the doping of 100 donor atoms. I did the doping of 100 donor atoms. So 100 donor atoms are supposed to give me 100 electrons. These 100 donor atoms at 0 Kelvin all will be there at the donor energy level. So all the 100 electrons will be coming here. And as we get the temperature, just as we get the temperature, what will happen is that they will move here. But we are not getting enough temperature that all the hundreds are moving here. 5% are neutral. What does that mean? 95% are ionized. So 5% neutral means either this language could be written 5% neutral, or this language could be written that 95% are ionized. Okay. So 100 donor atoms were supposed to give me 100 electrons, but they only give me 95 electrons at this particular temperature. Whatever the temperature is, I don't know. So rest 5% of the electrons are there at which position? They are there on the donor energy level only. So donor energy level is having 5% of the electron. So what is the probability of finding an electron at donor energy level? What I am saying? Tell me the probability of finding an electron at donor energy level. What do you think? What will be the probability? That would be equal to 5%, right? 0.05. Because out of 100, 95 have been ionized. That means 95 has reached to the conduction band. Only 5 are left on the donor energy level. So probability of finding an electron on the donor energy level is 0.05. Can I apply this formula now? Which formula? The approximate formula that we write down, e to the power minus E minus EF by KT. This is equal to 0.05. And in place of E, I am putting ED. Because what I am saying is that probability of finding an electron at donor energy level ED, that would be equal to e to the power minus ED minus EF by KT. Is this statement correct or not? Wrong. Why is that so? Because this function is defined for energy state, not for energy level. Till this point, we were using energy level and energy state simultaneously. Like sometimes I would call energy level as energy state, sometimes I would call energy state as energy level. But both are the different thing that you know. And here there is a difference. Why is that so? Because degeneracy factor is 2. That means on the donor energy level, you are having two states. So let's just say finding a guy on this floor is having a probability of 0.1 or 0.05. The probability that the guy will be there on this floor, that probability is equal to 0.05. So what is the probability that he will be there in this room? That means he can either be there in this, he can be there either in this room or in this room. So what will be the probability? Divided by 2. Are we able to understand this point or not? So probability of finding an electron at donor energy level is 0.05, but probability of finding an electron at donor energy state is equal to 0.05 divided by 2. Say yes or no? What I am saying, probability of finding an electron at one of the donor energy state because there are two states, so 0.05 divided by 2. And now this could be equal to, like this was wrong. So this 0.05 divided by 2 could be equals to this particular probability. Why is that so? Because Fermi direct distribution is defined for the energy state, not for energy level. That's why I was focusing again and again on that particular point, that it is defined for the energy state, not for energy level. Okay. So now I can write down f of ED is equals to 0.05 divided by 2, and this will be approximately equals to e to the power minus, because we can apply our approximation, e to the power minus ED minus EF by KT. How I am writing down this thing? From this formula only, 1 upon 1 plus E minus EF by KT. So sir, this thing goes upward, so e to the power minus E minus EF by KT. So minus, in place of E I am putting ED, that is equals to 0.05 divided by 2. So this was the beauty of this question. Although everyone solved this question using the formula, there is a certain formula that is given in our particular book, that is Niemann. You put that formula, you get the answer. But how many formulas will you remember? I will not even tell you that formula. Okay, so it's not practically possible to remember all this formula, and who knows, this question would be coming or something else would be coming, because I have framed another problem here. Now here different formula will be used. So will you mug up that formula as well? No. We will understand the concept, right? That's why here as well, in these questions, whatever that we studied previously, whatever the formula that we studied, there also I tried to give you the concept, not the formula, right? So here also we are not going to use the formula, we are going to use our concept. So let's solve it. KT value is 20 millivolt given, so don't do that error. Okay, KT value is 20 milli electron volt that you need to use, because 20 is given here. Usually we use 26, right? But here there is something difference. So let's find out ED minus EF. So take your calculator, ln into 0.020, 0.07 electron volt. This is what you are getting, ED minus EF. And what is given? EC minus EF is given. So from here, can you find out the value of what I need to find? EC minus ED I need to find, EC minus ED. So from here I can see that EC minus ED will be 0.25 minus 0.7, that would be equals to 0.18 electron volt. There you go. Okay, easy question, but you should know the meaning of degeneracy factor. If you know the meaning of degeneracy factor, then you can think in this manner, that on donor energy level there is a probability that 5% of the electrons could be there, that means 0.05 probability, right? And on this level, if there is 5% probability, that means on one of the states the probability will be 5% divided by 2. All good? Let's go to this question. This is from Niemann only, but we are not going to apply any formula, we are going to solve with respect to pure concept. Think about it as much as you can think. Whatever you can think about it, you will be able to get it. Silicon semiconductor doped with Nd. Nd is equals to 10 to the power 16 centimeter cube. 300 Kelvin. Now donor energy level is lying 0.05 electron volt below the conduction band. So this is my conduction band and this is my donor energy level. They are talking about that donor energy level. So conduction band and this is your donor energy level. The difference is 0.045 electron volt. The effective density of states is given. Degeneracy factor is also given. The degeneracy factor of a donor energy level is 2. What does that mean? That means on this donor energy level, you are having 2 rooms. Find the fraction of electrons still occupying that donor state. So what you did, you had 10 to the power 16 centimeter cube inverse, these many donor atoms you were having. So you thought that I should be getting 10 to the power 16 electrons. Basically here Ni value is not given, so you would say that number of electrons will be approximately equals to Nd. It should be approximately equals to Nd, right? Or should I write down Nd plus? I should write down Nd plus, because out of these 10 to the power 16 electron, some electrons have reached here and some electrons have stayed back to ED only. Let us say these were 100 electrons. So out of 100 electrons, it might happen that 99 electrons has reached here, but 1 electron is there in the donor energy level only. So I am writing n equals to Nd plus. That means whatever that has been ionized. Are you able to understand this point? Whatever n equals to Nd plus means the number of electrons that has reached to the conduction band. So what is n here? Number of electrons present in the conduction band. What is n? Number of electrons present in the conduction band. So this is number of electrons present in the conduction band. So at least one equation I can write down. N equals to Nc, right? N equals to Nc e to the power minus Ec minus Ef by Kt. This is one equation I have written. Okay. Now just think about it. What will be the probability of finding the electron on donor energy level? So should I write down donor energy level or donor energy state? Donor energy state, right? If I am saying that, what I am saying, on donor energy level there are Nd electrons. What I am saying, let on donor energy level there are Nd electrons left. Nd electrons left. Behind the electrons still occupying electrons left. What does that mean? That means these are unionized because they did not get ionized. Or you can, if you want to use the language of this particular question, then you can write down neutral. Okay, or I am writing down unionized atoms. So one thing you know here is that N plus Nd, number of electrons that are present in the conduction band and number of unionized electrons, those will be combined equals to capital Nd. Do you agree to this point or not? Right? All good? Number of electrons present in the conduction band, number of unionized electrons in the donor energy level, both combined will be equals to the total electrons that we were supposed to get. Right? Now what I will do is that I need to find some relation of Nd. Basically, I have find out the number of electrons present in the conduction band. Now I need to find out the number of electrons present in the donor energy level. What is my target? My target is finding out the electrons present in donor energy level. Donor energy level. This is my target, that is equals to Nd. So I need to find out the value of Nd now. Now what is the probability of finding an electron in donor energy state? Because I know the formula for probability and for the state, not for the level. What I am saying, probability of finding an electron at donor energy. What should I write down? Donor energy level or donor energy state? Donor energy state, because I know the formula for donor energy state, not for donor energy level. Are you able to understand this point? What I am saying is that I know the formula for donor energy state, not for the donor energy level. Basically, this formula that I write down, f of Ed, is it there for the level or for the state? It is there for the state. So probability of finding an electron on the donor energy state is given by e to the power minus Ed minus Ef by Kt. Right? Now on donor energy level you are having two rooms. On donor energy level you are having two rooms. Probability of finding the electron on this room is P1 and probability of finding the electron on this room is P2. So what will be the probability of finding the electron on this level? P1 plus P2. What I am saying, on this floor there are two rooms. Probability of finding a person in this room is 0.04 and probability of finding a person on this room is 0.03. what will be the probability that this guy will be lying on this floor? That means either he will be here or here, both will be added up, right? All good? Although there is a condition that they should be mutually exhaustive, but those mathematics we don't need to go, like don't apply PA plus PB minus PA union B. Those things we don't need to do, that they are mutually exhaustive event. They are exhaustive only. Basically, probability of finding an electron on this energy state is P1, and probability of finding an electron on this energy state will also be P1 only, because both are there on ED only. So what I am putting, probability of finding an electron at donor energy state is F of ED equals to this. Then what will be the probability of finding an electron at donor energy level? That would be twice of that. What I am saying, probability of finding an electron at donor energy level, what that would be? That would be twice of this, twice of this, 2 into ED minus EF by KT. Guys, look, it would have been very easy if I just write down the formula and I tell you to remember that. You remember this formula, okay, and then apply this formula, you will get the answer. You can find the formula anywhere on internet, but these things require understanding, right? So you have to appreciate that I am explaining this much. Otherwise, everything could be written in the textbook and formula is there, you remember it, in the examination question comes, you apply it, and then you will be forgetting it and you will not get the correct answer. But you are learning here what we are doing. What we have done now, we have find out the probability of finding an electron at donor energy level. Why we are doing so? Because now I can comment on that how many electrons will be there on the donor energy level. If I know the probability, then surely I can comment on the number of electrons as well. How? How did you comment on the number of electrons present in the conduction band? How did you comment on that? You said that, sir, probability is F of EC and number of states available are NC. So I multiply with them. Now probability of finding an electron is something this we have find out. Okay, that I am calling as P. Okay, P of ED. This I am calling as P of ED. So P of ED, this we have find out. What I should multiply it with so that I get the number of electrons present on the donor energy level? What I should multiply it with? With ND only, no? What I am saying is that initially, let's just say I was having 100 donor atoms. Now these 100 donor atoms have two chances, that either it can go on this floor or it can go on this floor. This floor was conduction band and this floor was donor energy level. Now I don't know anything about this, but I know that probability of finding an electron here is PED. What I am saying, probability of finding an electron on this donor energy level is PED. Let's just say this probability was 0.4. That means out of these 100, multiply with 0.4. That means out of these 100, 40 would have gone here and 60 would have gone here. Do you agree to this point or not? What I am saying? There are 10 to the power 16 donor energy, 10 to the power 16 donor atoms we are having. So let's do with the real calculation. 10 to the power 16 per centimeter cube, these many donor atoms we are having. It has two chances, that it can either go on the conduction band or it can go on the donor energy level. As of now, we are not talking about the conduction band, because we know that how many electrons will be there on the conduction band, that we have written down. How many electrons will be there on the donor energy level? That thing we need to find out. So that is equals to ND, small nd, that is equals to small nd. Now I know the probability of finding an electron here, that is given by PED. So probability of finding an electron on donor energy level is given by PED, that I know. So what I will do, I will multiply it with 10 to the power 16 so that I can get the number of electrons present on the donor energy level. So number of electrons present on the donor energy level will be given by ND. I hope you have got the point. Multiply with PED. Very soon this is coming in the examination, okay, very soon. And believe me, when the answer would come, you would see people applying the formula, blindly applying the formula, not even understanding what does the question mean. Okay, so we are not like that, we will understand it. We are not going to apply any formula. Okay, so This PED value I already know, ND value I already know. 2ND. Basically, PED is twice of something, no? So these two I have taken outside, and now I will just simply write down ED minus EF by KT. So this is the value of ND I am having. Equation 1, 2, and this is equation 3. Along with that, what value you have? N value you have. That is NC e to the power minus EC minus EF by KT. Now just let me know what you are supposed to find out. This was your equation 1 only, right? Equation 1 only. What you are supposed to find out? Find the fraction of electrons still occupying the donor state. Fraction of electrons still occupying the donor state. What does that mean? The total electrons were ND. Out of these total electrons, how many electrons are there on the donor energy level? Small nd. So this is something I need to find out. This is my target. So capital ND divided by small nd I need to find out. Okay. So let's do it. Let's do it on a page that I need to add. Small nd divided by capital ND I need to find out. So our target is to finding out this thing, right? So what I can do, this can be written as ND plus N, right? Capital ND is equals to small nd plus N, whatever the electrons that are there in the conduction band plus whatever the electrons that are there in the donor level. Now what I will do, I will divide by ND on both of the sides, on numerator and denominator. So this is what I am left with. So if I get the value of N by ND, my job will be done. So can I get the value of N by ND? Yes. That would be equals to NC by 2 ND, N by ND I am doing. So NC by 2 ND e to the power, here minus EC you are having, minus EC plus EF minus ED plus EF. So ED minus EC you will get, right? ED minus EC you will get. ED minus EC divided by KT. Just you need to divide. I hope you can do this process. It's not that tough, right? So N by ND I need to get, that I am getting NC value 2.8 into 10 to the power 19 and 10 to the power 16. 2.8 into 10 to the power 19. 2 into 10 to the power 16. ED minus EC. EC minus ED value is given, no? EC minus ED value is given. Yeah, EC minus ED value is given 0.045. So here negative value I will put. Divided by 0.0259. So you do this calculation, N by ND value you will get 0.045 divided by 0.0259 plus minus e to the power into 2.8 divided by 2 into 10 to the power 3. 246.35 we are getting. So from here if I find out ND by capital ND, that is equals to 1 plus 246.35. So add 1 and then take the reciprocal. So answer is coming out to be 0.0041, roughly around this much. This is the answer. This is the answer. And if they are asking in the percentage, so what will be the ND by N percent? Like how many percentage of electrons have been still not ionized? So how many electrons, how many percent of the electrons is still not ionized? 0.041. So that means you can call it multiply with 100. So 0.41%. So what does that mean? 99.59 99.5%, 99.59% have been ionized and 0.4% are neutral. Did you understand this question or not? Okay, so this question was just the opposite of this particular problem, just the opposite of that, opposite process only we are doing. although although here you need to think more, right? Here you need to think more what is happening. So all these process, whatever that I told you, just watch this question again, and a very good question for your practice purpose. Okay, so you must have understood a lot of new things here. Well and good. So yeah, these two questions we have done. These two are very good question. Let's move to our next topic. We are going to draw the energy band diagram for semiconductors. Okay, so first we will take the case of uniform, then we will take the case of non-uniform. In uniformly doped semiconductor, we will see two cases. One will be under equilibrium and one will be under external bias, or you can say non-equilibrium. Okay, equilibrium means that there is no external bias, uniformly doped it is. Everywhere it is uniformly doped. So it is, if it is uniformly doped, then have we seen the diagram already? Yes, conduction band, valence band, intrinsic Fermi level, and then something else. What I mean to say is that all the diagram we were seeing with respect to distance only, no? Basically we were drawing energy with respect to x. So there was conduction band there was valence band, and for intrinsic semiconductor, where was your Fermi level? It was somewhere in between, somewhere in the middle, conduction band and valence band. And what about for n type? For n type, what was the scenario? For n type, all these things are same, conduction band, valence band, but where was my Fermi level? Fermi level was near to my conduction band. Fermi level was near to my conduction band. Also, just for the reference purpose, we will always make the intrinsic Fermi level as well. Although it is not useful here, because your semiconductor is not intrinsic, it has become n type, but still for the reference purpose, we will always make the intrinsic Fermi level. Okay, always we will make it. And what about the p type? Conduction band is there, valence band is there, and where will be your Fermi energy level? It will be near to the valence band. And for your reference purpose, we will always make intrinsic Fermi level as well. So these things I already know. So these I have already studied. More doping means it will be more near to the valence band. More doping means it will be more near to the conduction band. These things also I already know. And with respect to the temperature variation also I know. So this we are drawing energy versus distance. Right? All good, all fine. Now what will happen if I give external bias? So let's write down a few things. We will write it down for the electrons. So you know that electrons will be there in the conduction band, right? This is the conduction band. Electrons will be in the conduction band. What will be the energy of the electrons? That would be equal to EC. If your electrons are there on the EC energy level, that means it is having an energy of EC. And what that would be equal to? That would be equal to the charge. Charge on the electron will be negative. Charge on the electron will be negative. Multiply with the applied potential. Do you remember? Energy is equal to QV. So applied potential I am saying is V0, and what I mean to say is that this is your semiconductor, and what we are doing, we are applying a battery across it, because under external bias, that means we are applying some battery across it. So this battery that we have applied, that is having a potential of V0. That means electron are getting a potential of V0 across them, and they are having the negative charge. So E is equal to, energy is equal to QV. So negative charge, applied potential is V0. This is any random semiconductor, it could be anything, intrinsic, n type, p type, whatever it is. Okay, so EC is equal to minus QV0 I can tell, because electrons will be there in my conduction band. So minus QV0, this thing I can tell. Okay. And one more thing I am telling, from now onwards, energy will be written as this kind of E, and your electric field will be written as this kind of E. Okay, this E and this E both are different. Energy, this kind of E, electric field, this kind of E. So this is your one formula. What will be the formula of electric field? Electric field is given by minus dV node by dx. I am assuming that this is my x equals to 0 and this is my x equals to L. So direction of electric field is always in the decreasing direction of the potential, right? So from here what do I see? This V0 will be equals to EC by minus Q. So what I can do from equation 1 and 2, minus dy dx In place of V naught, what I can put? EC by minus Q. EC by minus U. So minus sign will get cancelled out. Q is a constant. So what is the electric field we are getting? Electric field we are getting is, look, basically V naught can be a function of x. What I mean to say is that V naught can be a function of x, right? It will be changing with x, no? At x equals to 0, the potential is V naught. At x equals to L, the potential is 0. So it is changing with respect to x. So this is a function of x. This is a function of x. So V naught is a battery, but Vx is a function of x. So here I should write down Vx. Because this V naught potential, basically if I make the diagram of Vx, how the diagram of Vx will look like? The diagram of Vx. Vx is the potential across my semiconductor. So Vx diagram will look like something like this. That at x equals to 0 it is V naught, and at x equals to L it is 0. So this is how the diagram would look like. Right? This is how the diagram would look like. From V naught to 0 it is going, Vx versus x. Okay. So if if your potential is a function of x, then your EC will also be a function of x. Right? This is a function of x. So EC is also a function of x divided by Q. Minus sign is already there. So minus to minus will get cancelled out. 1 by Q. Q is a constant. So 1 by Q d by dx EC of x. This is what you are getting. Right? So similar thing will be there for the holes as well. It will be there for the electrons as well. So whether it is p type, n type, whatever it is, electric field is proportional to the slope in the conduction band. Electric field is proportional to the slope in the conduction band. Okay. So this thing we have derived. So I am saying that this particular thing will be there for the electron holes for both of them. So electric field will be for both electron and holes. For both electron and holes. So this is a very important relation, very important. Electric field is equals to 1 by E dEcx by dx. Now at your level, in your examination, at your BTech level, always the slope of conduction band, valence band and intrinsic Fermi level will always be same. What I am saying? The slope of conduction band, valence band and intrinsic Fermi level. What I mean to say is that whatever the picture of conduction band you will get, let's just say picture of conduction band is somewhat like this. So the same structure you will get for intrinsic Fermi level and the same structure you will get for valence band as well. Basically EC, EFI and EV will always look the same. Always it will look the same, 100% I am telling. So whatever that is happening for EC, the similar thing will happen for EF as well. And the similar thing will happen for intrinsic Fermi level as well. Are you able to grasp it or not? So this is the formula that you need to remember. It is very easy to remember. You will not even have to mug it up. Why so? Let's see it. What is the unit of electric field? Volt per centimeter. Right? What is the unit of energy? Electron volt. Sir, what do I need? Volt per centimeter I need. So that means I need to divide by centimeter. That means energy should be differentiated with respect to x. Then you will get electron volt divided by centimeter. Now you need to kill this electron. That means you need to kill the charge. So divided by 1 by q. Electric field is having a unit of, sir, volt per centimeter. Voltage divided by the distance. Volt per centimeter. Volt per centimeter I need. I have electron volt, that is energy. Per centimeter, that means I need to differentiate it. Sir, electron I need to cancel out. Volt per centimeter I need. So divided by q. So E equals to 1 by q d by dx. There you go. So here I am writing down one statement. What is that? Arey yaar. Just a second, guys. I need to put the charger. Yeah. So here I am writing down one statement. What is that? Your electric field is proportional to d EC by dx. Or you can say it is proportional to d EV by dx. Or you can say it is proportional to d EFI by dx. Again, a very important conclusion. Let's remove it off. Let's write it down here. Very, very important conclusion. How will you say it in the statement? How will I say it? In the direction of electric field, what I am saying, in the direction of electric field, the slope of conduction band will increase. In the direction of electric field, here positive sign is there, no? E is equals to minus dV by dx. The potential is decreasing in this direction. The potential is decreasing in this direction. That means what is the direction of electric field? This is the direction of electric field. Is this the same? Yes. Here there is positive, here there is negative. That means this is the direction of electric field. Right? Because there was a negative sign here. But now if I say this is the direction of electric field, then what will be the slope in the conduction band? What do you think? This will be the slope, no? Because in the direction of electric field, the slope of conduction band will increase. Or I should not say slope will increase, I will say slope will be positive. In the direction of electric field, the slope of conduction band will be positive. Just write it down somewhere. Here you can write down. In the direction of electric field, the slope of the conduction band will be positive. Here in the direction of electric field, this was the direction of electric field. So in the direction of electric field, the slope of voltage was negative. In the direction of electric field, the slope of voltage was negative. That's why the relation was E is equals to minus dV by dx. But here there is a positive sign. So in the direction of electric field, the slope of conduction band will be positive. Say yes or no. Write it down somewhere. All good? All fine? Next, one more statement is there. So this this statement we kind of prove it, right? We proved it. We proved this statement here. But next proof I am not going to give. So in n-type semiconductor, the current will be in n-type semiconductor, the current will be proportional to d by dx of EFN. And in p-type semiconductor, the current will be proportional to d by dx of EFP. What does that mean? In the direction of current, the Fermi energy level will have the positive slope. Sir, where is the proof? We will see it when we study PN junction. In PN junction, we will see the proof. Okay. As of now, you don't need to see the proof. As of now, what you will say? Sir, in the direction of electric field, the conduction band, valence band and intrinsic Fermi energy level will have the positive slope. What I am saying, in the direction of electric field, conduction band, valence band and intrinsic Fermi level will have the positive slope. And in the direction of current, the Fermi energy level of n-type and p-type semiconductor will have the positive slope. You don't need to mug it up. Very easily you will be able to understand when we see the examples. Okay. So for every possible circuit, we are going to draw the energy band diagram. Like whatever the energy band diagram that we are going to discuss in this video, those only can be coming in your examination. Nothing apart from that would come. And that is my 100% guarantee. So whatever that we are discussing, those only will come. Okay. So just have the patience and keep on looking at it with the like a lot of method. By using a lot of method, I will tell you the energy band diagrams. So previously there was no battery involved. Now what I am doing is that I am involving the battery. Okay. So this is your intrinsic, this is your n-type and this is your p-type. In intrinsic, previously what was the scenario? This was the scenario. Right? When there was no battery involved. Now what is happening? Battery is being involved. If battery is being involved, so what will happen? Here positive potential will go and here zero potential will go, or you can say negative potential will go. Let's talk about the electrons. Here there are electrons. What is the energy of electrons? Q into V naught, right? Minus Q into V naught. So positive charge that is coming and electrons are having the negative charge. So positive charge multiply with the negative charge. Positive potential multiply with the negative charge. What will happen? Energy will go down. Are you able to understand this point? What I am saying, positive potential multiply with negative charge. What will happen? So energy on this end, energy at x equals to 0 is going down. Energy at x equals to L. energy at x equals to L. Here there are electrons as well. Here there are electrons as well. So electrons are negatively charged and potential is also negative. So negative potential multiply with the negative potential, total will be positive. So energy here is going up and energy here is going down. So this was your conduction band. Now what is happening? This energy is going down and this energy is going up. So this will become your conduction band. And what did I tell you? In the direction of electric field, the conduction band will have the positive slope. In the direction of electric field, what is the direction of electric field? This is the direction of electric field, right? Because positive charge is coming here, negative charge is coming here. So this is the direction of electric field. So in the direction of electric field, conduction band is having positive slope. So by two method we are understanding it. One is, sir, here positive potential is coming, here positive potential is coming. This is about the energy. So positive potential is coming, multiply with the negative charge. Energy is equals to minus Q into V naught. Positive potential multiply with the negative charge. Sir, what is happening? Energy is decreasing. Negative potential multiply with the negative charge, energy is increasing. So conduction band at this end, at x equals to 0, it will have lesser value, and at x equals to L, it will have more value. So this is what I am drawing. I am drawing the graph of energy versus x. Energy versus x. So this is your energy is shown by capital E versus x. So this is your x equals to 0. This is your x equals to 0. At x equals to 0, the energy has decreased, and at x equals to L, the energy has increased. Right? This was your conduction band. Now, although I know that whatever the slope is there in the conduction band, the same slope will be there in the valence band and same slope will be there in the intrinsic Fermi level. But still, let's understand more things. How will I understand? Let's remove it off. Now I need to see the slope in the valence band. What I am saying? I need to see the slope in the valence band. Okay. So when I say valence band, what should come in your mind? Sir, when I say valence band, in my mind, holes should come. So in my mind, holes are coming. When I say valence band, holes are coming. Here also holes are there. Here positive potential is reaching and here negative potential is reaching, right? Positive potential, negative potential. What will be the energy of holes? That would be, sir, positive charge multiply with the positive potential. At this particular end, what will be the energy of holes? Sir, positive charge multiply with the positive potential. That means here the energy is more. For the holes, at this end, at x equals to 0, the energy is more, and here the energy is less. For holes I am saying, because holes are having the positive charge. So positive charge multiply with the positive potential, energy is more. Positive charge multiply with the negative potential, energy is less. So sir, here energy more, here energy less. This is how I should make the diagram. No, the energy of holes increases in the downward direction. So if there is more energy, that means this point, here there is more energy, so this point will be downward, and here there is less energy, that means this point will be upward. So this will be the slope in the valence band. That's why I said that the slope in the conduction band and valence band will always be same. Although you don't need to remember all these points to solve the question. To solve the question, what you need to do? In the direction of electric field, the slope in the conduction band, valence band and intrinsic Fermi level will be positive. That we have already seen here. But if you are understanding that what is actually happening, this is what I am telling. What is actually happening? There are electrons as well, there are holes as well. For the holes, what will be the scenario? Holes are having the positive charge, multiply with the positive potential. Energy will increase. In case of holes, getting more energy means going downward, because energy of holes increases in the downward direction and energy of electrons increases in the upward direction. Do you understand this point or not? Right? So this particular point is having more hole energy and this particular point is having lesser hole energy. So this will be the slope, this will be the scenario for the valence band, and then I will make the intrinsic Fermi level somewhere in between. This will be your EFI. Okay, so you can simply see, if this question was coming in your examination hall, what you would have done? You would not think, sir, electrons, holes, positive potential, negative potential, nothing. make the electric field. In the direction of electric field, the slope of conduction band will be positive. Whatever the slope is there in the conduction band, same in the valence band, same in the intrinsic Fermi level. In some rough notebook, somewhere in your rough work, you can write down all the things that I told. Positive charge, positive potential, negative potential, both applied, energy increases, energy decreases. So here there is less energy for electrons, here there is more energy for electrons, here there is more energy for holes, here there is less energy for holes. Okay, well and good. Although no one will ever ask you the energy of holes. Why so? Because holes are not a particle. In the examination, it will never come that, sir, at this point, energy of holes is more. This thing will never come actually. Why so? Because holes are not a practical particle, no? Or it might be asked, like in theory examination, anything it could be asked. They will make the diagram and they will ask you at this particular point, they will give this energy level as EV1 and this as EV2. So which is representing more energy of holes, EV1 or EV2? So EV1 is greater than EV2, right? For in case of holes. So these things they can ask. In the theory examination, anything could be asked. So every concept should be clear to you. Although I cannot write down all the things, that positive charge will be multiplied with the positive potential, so energy increases. So all these things you need to write down on your own. Notes will be made like this only. Okay. Only thing I can tell is that this is the direction of electric field. In the direction of electric field, the slope of conduction band, valence band and intrinsic Fermi level will be positive. Okay. Let's go to n-type. Here as well, you can make the diagram very easily. How you can make the diagram? So first I will make the diagram how I would have done in the examination hall. How I would have done? Sir, positive, negative. What is the direction of electric field? Sir, this is the direction of electric field. Previously, I have proved that, sir, in the direction of electric field, all these slopes will be positive. In the direction of electric field, all these slopes will be positive. That means conduction band energy will be increasing like this, sir, like this, and somewhere, sir, right in between, right in the middle, there will be intrinsic Fermi level, sir. Arey wah. Now, sir, second thing, what do I know? Sir, this will have some EFN as well, right? It will have Fermi level for n-type. That will be here. Now you know that, sir, what will be the direction of current? This will be the direction of current. This will be the direction of current in n-type. This will be the direction of current in the n-type. So direction of current is this. What is the direction of current? In the semiconductor, what is the direction of current? This is the direction of current. So this shows the direction of current. In the semiconductor, this is the direction of current. So in the direction of current, the slope of Fermi energy level will be positive. That means in the direction of current, the slope of Fermi level will increase. In the direction of current, the slope of Fermi level will increase. There you go. This will be your EFN. So this diagram you will get. EC, EV, EFN, EFI. If I ask you one more question, or let's not do it here. Okay, I will frame different question. Otherwise, like diagram will be very complex. You will not be able to understand, sir, from where these things come into action. So let's not do anything here. I will simply ask another question in some other problem. So as of now, you are able to understand what is happening, right? Voltage, then electric field direction. In the direction of electric field, conduction band, valence band, and intrinsic Fermi level will have the same slope, or it will be increasing. And in the direction of current, the slope of Fermi energy level will also be positive, or you can say the Fermi energy level energy will also be increasing. All good? All fine? Okay then. And if I ask you, sir, this gap and this gap, will that be same? Yes. Basically, all these lines are parallel. All these lines are parallel. Why so? Why so? Because you know that the gap between conduction band and the Fermi energy level shows, what does it show? Shows the level of doping. Like if the gap is lesser, if I am saying that gap is lesser here and gap is more here, this is your EC, this is your EFN. So if I say there is lesser gap here and more gap here, what does that mean? That means at x equals to 0, this is your x equals to 0, right? And this is your x equals to L. So that means that at x equals to 0, there is more doping, at x equals to L, there is lesser doping. But is that the scenario here? No, because it is uniform doping. We are studying the case of uniform doping. That means both of these lines has to be parallel in case of uniform doping. That's why whatever the slope is there in the conduction band, the same slope is there in the Fermi energy level as well. But in case of non-uniform doping, you will get this kind of diagram. There at one particular level, you will be having more doping. At other x equals to L, you will be having lesser doping. That means one will be near to the conduction band, other will be further from the conduction band. Near to the conduction band means more doping. Farther from the conduction band means lesser doping, right? So although till this point everything is going very smooth, you can do the same for p-type semiconductor as well. What you will see, sir, positive will go here, negative here, sir. This is the direction of electric field, sir. No Jarda here, okay? No Gutka, no Ajay Devgan, only elaichi, so that my throat doesn't pain much. As a teacher, all these things comes into action, like throat pain, regular cough, you can see, headache. So when you speak too much, like when I explain, like I get so much of energized, right? You would have seen, मैं बहुत ज़्यादा एनर्जी लगा देता हूँ एक बार एक्सप्लेन करने में, तो उससे दिक्कतें हो जाती है, ठीक है? तो गुटखा वगैरह नहीं खाता हूँ मैं, राजस्थान से, उसका मतलब ये नहीं कि बोलो जुबा केसरी, ठीक है? जुबा केसरी वगैरह नहीं है, ऑल्दो हम बेचते हैं यार, गुटखा बेचते हैं, ठीक है? हर मारवाड़ी गुटखा बेचता है भाई, बहुत बिकता है यहाँ पे, या तो गुटखा नहीं जवा रहा हूँ मैं, इलायची जवा रहा हूँ, ताकि आपको प्रॉब्लम ना हो, मैं ज़्यादा कहाँ सुना. तो इन द डायरेक्शन ऑफ इलेक्ट्रिक फील्ड, this will be your conduction band. A same diagram would come, no? So what I am doing, I can simply copy it, but I will just have to remove EFN. What I will have to remove? I will just have to remove this one, because here EFP would come. So here EFP would come and it would be near to valence band. Why so? Why this is the slope? Because what is the direction of current here? The direction of current is this only. This is the direction of current. This is your IN, right? Sorry, IP. In the direction of current, the slope of Fermi level will be positive, or you can say in the direction of current, EFP energy will increase. In that manner, it will increase. Increase for the electrons, decrease for the holes, right? If hole is at higher energy, like this is your energy versus X graph, and this energy I am telling for holes. So this is higher energy or this is higher energy? This is higher energy, right? This hole is having higher energy because it is lower, right? So energy increases for electrons, decreases for holes. So yeah, these are the diagrams. I hope you are able to understand very easily. In the direction of electric field, the slope of conduction band, valence band and Fermi energy level is increasing. In the direction of current, the slope of this Fermi energy level is increasing. Okay, so electric field is associated with this, and current is associated with this. Okay, well and good. So as of now, all the four are having the same slope. Yes, as of now, all these four are having the same slope. Why so? Because valence band and Fermi energy level, this gap should always be constant. Why so? Because there is uniform doping. If there is uniform doping, that means the gap between the valence band and the Fermi energy level should be constant. If there was more doping, that means the Fermi energy level will be near to the valence band, and if there is lesser doping, then Fermi energy level will be farther from the valence band, right? Okay, let's see our opposite potential I have applied now. Very simple thing. Positive potential will go here, negative potential will go here. So where will be the electric field now? Electric field will be there in this direction. Here also in this direction electric field. Here also in this direction electric field. What will be the direction of current? This will be the direction of current. This will be the direction of current, and this will be the direction of current. Why this is the direction of current? You are understanding, right? Holes will move in the opposite direction to the applied electric field. Then holes will move in the same direction to the applied electric field. Then from where the current would come. Although all these concepts are very initial, that we studied in the first lecture. So direction of current should be clear. Always the current will be flowing out of the positive terminal of the battery. always the current will be flowing out of the positive terminal of the battery. That's why I am very easily able to make the direction of current, 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 direction of current. Although here direction of current is not useful because here EC, EV and EFI only is there, right? EC, EV and EFI only is there, no? So here direction of current is not much useful because EC, EV and EFI will always have the same slope that I already know. So let's make the diagram very quickly, because now this is the direction of electric field. This is the direction of electric field. This is the direction of electric field. This is the direction of electron current. This is the direction of hole current. Somewhere in between EFI, EFI, EFI. So all these will have the same slope with respect to, it is coming because of the electric field, right? It is coming because of the electric field. Now coming to this diagram, current, and I know that since this is n type, so your intrinsic Fermi level will be, sorry, your Fermi level for n type will be somewhere near to the conduction band. So it will be here, and since this is the direction of current, so in the direction of current, the Fermi level will have the positive slope. Fermi level will have the positive slope, and in the direction of current, the Fermi level will have the positive slope. So this is the direction of current. In the direction of current, you should look. This is the direction of current. So in the direction of current, positive slope. So EF, it will be near to the valence band, and these gaps will always be same. Why these gaps are same? Because it is uniform doping, right? In case of uniform doping, the conduction band and Fermi energy level of n-type semiconductor will have the same gap because doping is uniform. Okay. Now, energy band diagram for non-uniformly doped semiconductor. So now the doping is non-uniform. So if there is doping, that means there is no meaning of intrinsic semiconductor. So now we are going to take only doped semiconductor. That means we are only going to take extrinsic semiconductor. So now this is the first case under equilibrium. That means there is no external bias. So this is your scenario, right? There is no external bias. So what will happen here? The electron will start diffusing here, right? Because of this diffusion, because of this electron are starting to diffuse here. Electrons are diffusing here. Because of this diffusion, what is happening? There is this diffusion current coming into action. Now let me use a different color of pen. So because of this diffusion current is coming into the action. This all the process is clear to you, okay? And because of this, what really happened? There was a built-in electric field build-up. There was a built-in electric field build-up. Now because of this built-in electric field, electrons are being drifted in this opposite direction. So electrons are being drifted in this opposite direction. So electrons are drifting here, and since they are drifting here, then there is a drift current in the opposite direction to the diffusion. So there is a drift current in the opposite direction to the diffusion, and this diffusion and drift current is cancelling out each other, right? And since they are cancelling out each other, so total current is 0 here. So what is the total current? Total current is 0, but total electric field is not 0, no, right? There is a built-in potential developed. Here there is positive charge and here there is negative charge. So your semiconductor, your n-type semiconductor is feeling a built-in potential. So E built-in is there, and in the direction of electric field, the slope of conduction band will be positive. There you go. Positive. Slope of valence band will also be positive, and slope of intrinsic Fermi level will also be positive. There you go. Conduction band, valence band, intrinsic Fermi level. Did you understand from where the slope came? Because of this built-in electric field. Okay? Because there is an electric field, that means here there is positive potential. If here there is positive potential, that means electron energy will decrease, and here electron energy will decrease. Here there is positive potential, that means positive charge multiply with the negative charge, energy will decrease. Positive charge, here there is negative charge multiply with the negative charge, energy will increase. So here less energy, here more energy. So this is the slope. But will there be any slope in the Fermi energy level of n-type? Will there be any slope here? No, 0 slope. This is your EFN. Why there is 0 slope? Because you know that the slope in EFM is proportional to the current. and this current is 0, and since it is 0, then EFN will be constant, or you can say uniform. Better you should say uniform, because it is with respect to x. So I should say uniform. Are you able to understand this point or not? And this is telling another important thing. What is that? Here the gap between EC and EFN is less, and here the gap is more. If the gap is less, that means more doping, and if gap is more, that means less doping. Are you able to relate everything now with respect to energy band diagram? So this energy band diagram we are drawing with respect to x, right? With respect to x. With respect to x, and this is your energy. So energy with respect to x. So at x equals to 0, you can see that there is more doping. So if only this diagram was given, what I could have said? If there is no slope in the Fermi energy level, that means there is 0 current. If there is 0 current, what does that mean? There is no external battery applied. Yes, first conclusion. Second conclusion, there is a slope in the conduction band in this direction. What does that mean? That means electric field also be in this direction only. Conduction band energy is increasing in this direction. So in the increasing direction of conduction band energy, there will be electric field, because electric field is positive in the electric field, the direction of electric field will be in the increasing direction of EC. So this will be the direction of electric field, and if this is the direction of electric field, that means here positive charge is developed, here negative charge is developed. That means here there would have been more doping, because positive and then there is electron. So here there would have been more doping, here there would have been lesser doping. Or you can directly see from here as well that at this point there would have been more doping, at this point there would have been lesser doping. So are you able to relate everything or not? What will happen in this p type? What will happen? Electrons will diffuse here. Total current I already know will be 0, right? What will be the direction of built-in potential? Here there will be negative charge, holes will be diffusing here. So this will be the direction of built-in potential. This will be your built-in potential, right? So this is your built-in potential. If this is your built-in potential, then what kind of slope you will be getting? Slope you will be getting like this, because here there will be negative, here there will be positive. So this will be the slope you guys will be getting. Conduction band, valence band, and intrinsic Fermi level. Okay. Now since the current is 0, what does that mean? Wait a second. क्या हो गया ये? Holes are diffusing in this direction. Okay. Yeah. Okay. Nothing. Now different color of band. Since there is 0 current here, what does that mean? Since there is 0 current here, what do I know? EFP divided by DEFP divided by dx. Slope in the Fermi energy level, slope in the Fermi energy level is proportional to the current. That means EFP will be uniform. There will not be any slope. So if EFP is uniform, what does that mean? That means this is how your EFP will look like. No slope, simple straight line. This is your EFP. And if this is your EFP, you can directly see there, here there is more doping and here there is lesser doping. More doping, lesser doping. So is that the correct? More doping, lesser doping. This was your x equals to 0 and this was your x equals to L. So if I just see this diagram, what I will see? First thing, okay, Fermi energy level is near to the valence band, that means it is p type. Second thing, electric field is in this direction, that means built-in electric field would have been developed in this direction. Just by looking at the slope, you can never tell whether it is built-in electric field or total electric field, because this represent about the total electric field. No, here did I write down built-in electric field? Did I write down external electric field? No, it is total electric field. So the slope in this one will represent the total electric field. So I cannot say that, sir, this will be the direction of built-in electric field. No, as of now I cannot make any current. But what I can see is that, sir, here there is more doping, here there is lesser doping. So I will make the diagram and I will get to know that yes, this is the direction of built-in electric field. Secondly, I can see that, sir, here there is zero slope. In the Fermi energy level, there is zero slope. What does that mean? Sir, there is no external battery. So only electric field that is left is built-in electric field. Are you able to understand this point? So all these two diagrams are clear. Now the most interesting part would come. The most interesting part would come. Now the most interesting part would come. Okay, we are going to connect the battery, but we are going to connect the battery in 3 different ways. Actually, in 6 different ways. Okay, so how we are connecting the battery? This is your N-type semiconductor. You agreeing to this? I have connected an external battery. Where will be my built-in electric field? This will be my built-in electric field, because I know that my holes will be diffusing here. So this will be your built-in electric field. And where will be your external electric field? Sir, this will be your external electric field, because you know that actually this is your V external. This is my V external. So here positive, negative. So this is my E external. So E external is in the opposite direction to E built-in. And now I am saying that built-in electric field is more than the E external. Built-in electric field is more than the E external. So when it was under equilibrium, what was happening? This built-in electric field was the reason, because of that diffusion current was cancelling out. Basically, how we started? Sir, electrons will diffuse. Okay, because of that diffusion current is coming into action. Because of that, we are getting built-in potential. And this built-in potential or this built-in electric field was the reason why we got drift current. And this drift current and diffusion current are cancelling out each other. So this built-in potential was enough to cancelling out diffusion current. What I am saying? What is the expression of diffusion current? What is the expression of diffusion current? That is Q dp dpx by dx. Does it depend on the electric field? This diffusion current, does it depend on the electric field? No, doesn't depend on the electric field. Doesn't depend on E field, right? So whatever the diffusion current you are getting here, the same amount of diffusion current you will get in this case as well. So diffusion current under equilibrium or diffusion current under bias, under external bias, both will be of the same amount. So this is my diffusion current. So whatever the diffusion current I was getting previously, the same amount of diffusion current I am getting now. A very, very important discussion. Okay, keep your full concentration here. Whatever the diffusion current I was getting here, the same diffusion current I am getting here as well, because it doesn't depend on the E field. So same as equilibrium. Same as equilibrium. Same amount as equilibrium I should write down. Not the direction, because someone will understand it is about the direction. No. Same amount as equilibrium current. Equilibrium. Okay. But what is happening with the built-in electric field? This is the direction of built-in electric field, and external electric field is in the opposite direction. And I know that who is winning? Built-in electric field is winning. So total electric field will be this E built-in minus E external. So this will be your total electric field in this direction. That will be E built-in minus E external. And because of this electric field, what will happen? Electrons will drift in this direction. Electrons will drift in this direction. And because electrons are drifting in this direction, there will be some drift current that will be flowing in this direction. I drift. But this drift will be lesser than this particular drift. Why so? Because this drift was coming because of EBI, because of the built-in electric field. But this drift is coming because of the built-in electric field minus some external electric field. That means this field is low. What I am saying is that surely your EBI is lesser than EBI minus E external. There is no doubt about that. That means this field is lesser than the equilibrium electric field. This field less than equilibrium. Less than equilibrium. That means this drift current will also be less than equilibrium. So this current is more and this current is less. that means what will be the effective direction of the current? So what I am saying here is that I diffusion is more than the I drift. So effectively diffusion current will flow in this direction. Effectively your diffusion current will be flowing in this direction. Are you able to understand this point or not? And eventually we expected that from the positive terminal of the battery current should go out. Yes, from the positive terminal of the battery only current is going out. A very important discussion, a great discussion. Nowhere in any textbook, in any lecture you are going to find this discussion. Just you need to think purely. So how did we think? Again let me start. Previously there was equilibrium condition, now I am connecting the battery. Since I connected the battery, this time I smartly connected the battery in the opposite direction to the built-in electric field. So now what is happening? Built-in electric field is actually getting lesser. If it is getting lesser, that means the drift current is getting lesser. Because of the electric field you get the drift current. And that is getting lesser, and diffusion current doesn't depend on the electric field. It will just depend on the concentration gradient. And whatever the concentration gradient you are getting here, the same concentration gradient was here as well. So same diffusion current is there. Same diffusion current is there. But the drift current has been less. So diffusion current will be winning. So diffusion current, here I should not write diffusion current. Diffusion current is winning. This actually current is, this current I is equals to I diffusion minus I drift. So total value of the current will be flowing in this direction. So this is the direction of current, and what is the direction of electric field? Effective electric field. Like this is the built-in and this is the external. So what is the effective direction? This is the effective direction. So here I will use this pen. So this is the direction of total electric field. The total electric field is equals to E built-in minus E external, because E built-in is more. So this is the direction of total electric field. So this is the direction of total electric field. That means this will be the slope in the conduction band, this will be the slope in the valence band, and intrinsic Fermi level will be somewhere in between. Intrinsic Fermi level will be somewhere in between. Conduction band, valence band, and intrinsic Fermi level will be somewhere in between. Now next, current is there, IN is there. So current is flowing in this direction. That means the Fermi level will have the slope in this direction. Fermi level will have the slope, positive slope in this direction, and this is having a slope in this direction like this. This is your EFN. And by default you can see that here there is more doping and here there is lesser doping. Are we agreeing to this? Yes. More doping, less doping, less doping. So it is coming by default. Here you need to make the increasing slope. So if I make the increasing slope like this, by default it is coming that here there is more doping, here there is lesser doping. Are you able to relate everything now or not? Every single thing is related. If this diagram is given, then you will understand everything. That sir, if there is some current, that means there would be some external bias. Okay, external bias is there, sir. You would know, sir, here there is high doping, here there is lesser doping. Second thing is also proven. Next, sir, I will see the direction of electric field. Total direction of electric field is this. So what I may think? I may think that, sir, since this is the total direction of electric field, so the thought that can be coming in my mind would be, sir, E built-in and E external are getting added. Right? Two things could be there. Either they are subtracted or added. So I thought that, sir, they are being added. And if they are being added, then, sir, I thought that total electric field will be in this direction. But if they are added, then what will be the potential of battery? The potential of the battery would have been like this. Then the current would have been flowing like this. And if the current would have been flowing like this, then the slope would have been like this. But the slope is this. That means the current is actually flowing in this manner. So potential of battery would be somewhat like this. And if potential of battery is somewhat like this, what does that mean? They are actually being subtracted. So looking at the diagram, I can make all the conclusion. Basically, looking at this diagram, I can make this diagram in the examination hall. Say yes or no. Okay. So how you are understanding the explanation? Like, how do you find the explanation? I hope you are enjoying. Right? Every single thing I am explaining with good amount of patience, and with every single thing I am writing down as well. So I hope it is crystal clear to you. Okay. Well and good. So yeah. Next thing is E built-in is equals to E external, and in the next case E built-in would be less than E external. Do it on your own. Do it on your own. E built-in equals to E external. That means whatever the built-in diffusion current, nothing is happening to diffusion current. It would be same. Whatever the case was there, this was the direction of diffusion current. Nothing is happening to diffusion current. Diffusion current is same. But since E built-in and E external both are in the opposite direction, and you are saying that E built-in is equals to E external, what does that mean? E total will be E built-in minus E external, and that would be equals to 0. So there is no electric field. If there is no electric field, no drift. So total current IN will be equals to I diffusion only. So again the total current is flowing in this direction, but there is no electric field now. If there is no electric field, then this will be the scenario. The conduction band. Wait a second. No. What I am saying. Yeah, no issue. Basically, let's make the semiconductor, and this was my battery, right? This was my battery. So total electric field is 0. Total electric field is 0, right? Total electric field is 0, but the current direction is this. This is your current direction. And total electric field, E total is equals to 0. There is no electric field. If there is no electric field, then what will happen? Conduction band, valence band, and intrinsic Fermi level. There you go. Conduction band, valence band, and intrinsic Fermi level. But the current is flowing in this direction. EFN. And you can directly see that here there is more doping, here there is more doping, and here there is lesser doping, here there is lesser doping. So this kind of diagram is also possible. No gutka. Okay. No gutka, only elaichi. So interesting diagram, right? Someone will see it directly. Okay, there is no electric field, but there is current. How it is possible? That means it is the case of non-uniform doping. If there is no electric field, that means our built-in and external would have been cancelling out each other. If they are cancelling out each other, then this will be the scenario. So if I will just make this diagram and I will ask you to make the conclusion that at x equals to 0 there is high doping, at x equals to L there is low doping, at the built-in electric field and external electric field are opposite in the direction and having the same amplitude. So these kind of points I will write down that which of the following statement is true. Okay, so in that manner question can be framed. So everything should be clear to you, and I hope it is clear only. Right? Now what is the scenario? E external is more. E external is more. Diffusion will say, sir, I will have my same thing. There is no one who can stop me. I will have my same thing, sir. This is my I diffusion. No one will. Here, writing down diffusion would be wrong. This is your I diffusion. Diffusion current will say, sir, I will be the same. There is no one who can stop me. But now, this is your E external, this is your E built-in. E external is more this time. That means E external will be winning. So total electric field will be in this direction. Total electric field will be in this direction. That will be E external minus E built-in. That means electrons will be drifting in this direction. Electrons will be drifting in this direction. This is drift of electron. If electrons are drifting in this direction, then what will be the current of it? This will be your I drift. Both are being added this time. Both are being added in this direction. So again you see this was your semiconductor. Again here there was more doping, here there was lesser doping, here also there was more doping, here there was lesser doping, and there was more doping. In that manner I am showing more doping. Okay, so this was your built-in electric field. This is your E external. E external is winning. E external is winning. So this will be the effective direction of electric field. So how the slope of conduction band, valence band, and all these things will look like. So this is the direction of effective electric field. So conduction band, valence band, and somewhere in between EFI. Right? Next, what I need to do, what is the direction of current? So drift and diffusion both are being added. So this is the direction of current, right? So sir, I will have to make slope like this. But now think about it, how will you make the slope? What I am saying is that someone will say that sir, I can make the slope like this. Someone will say that sir, I can make the slope like this. Positive slope only you need to make, no? And someone will say that sir, I will make the slope like this. Which slope is correct? In the direction of current, the slope will be positive, right? So you will say sir, both of those could be correct, but the slope would be like this only. Why so? Because here there is more doping. At x equals to 0 there is more doping, and here there is less doping. So this is your x equals to 0, right? And this is your x equals to L. So here there is more doping. So this is your EFN. Understood? Right? Write down the total electric field. This is your total electric field, and write down the direction of current and make the slope. Then make sure that more doping means near to the conduction band. That's it. Okay. So all these three cases, whatever the cases that can be asked in your examination, surely it is there in your notes. And next case would be very easy. Here you take E built in greater than E external or equal or lesser, but both are in the same direction. So now this is the direction of your E built in, right? And this is the direction of your E external. Both will be added. If both will be added, so diffusion will say, sir, I don't know, electrons will diffuse here and I will generate my diffusion current in this direction. Diffusion will say, sir, I am independent of the external bias. I don't care about the external bias. I only care about the concentration gradient. So diffusion is saying, sir, I am as it is. But now what is happening? Built-in and external both are being added. Built-in and external both are being added. That means total electric field is becoming very high in this direction. So electrons are drifting very highly in this direction. That means diffusion current will be very high in, drift current will be very high in this direction. Why so? Because when alone built-in was there, then diffusion and drift was getting cancelled out. When alone built-in was there, diffusion and drift are getting cancelled out. But now built-in plus external is there. So drift will say, I am having much more importance now. So what will be the total current? Your final IN current would be in this direction. This will be your final IN current. Do you agree to this point or not? So this will be the direction of your total IN current, right? Yeah, this is the direction of your total IN current. So in the semiconductor, it will be flowing like this. In the semiconductor, it is flowing like this. And this is the case for everyone, no? Either it is greater, lesser, or whatever it is, they are being added. So what do you see? This is your total electric field. This is my total electric field. Conduction, valence, EFI. And what about the direction of current? This is the direction of current. So slope will be positive in this direction. Look, this diagram will not become much of clear. Now it is fine. Right? Slope is positive in the direction, but I need to make sure that here there is more doping, here there is lesser doping. But slope is positive only. You can see slope is positive only. Slope is positive. Slope is positive. Okay. So making sure that slope is positive, along with that here there is more doping and here there is lesser doping. So this is your EFM. Direction of current is this only. So direction of the current is always, current will be flowing out of the battery. Current is flowing out of the battery. Current is flowing out of the battery. Current is always flowing out of the battery. Current is always flowing, here there is no current. So current will always flow out of the battery. So for the direction of current you will never have to think. Now we will do the same for the p-type semiconductor, and we will never have to think, sir, this external, internal, nothing we will have to think. Okay, and I will show you how to do it. So what we will do, this is for the p-type semiconductor. Okay, first case is built-in is more than, first thing I know that this is my external battery connected. So I know that this will be the direction of current. In all of the cases, this is the direction of current. What about the electric field? For electric field, I need to think. So this will be my built-in electric field. This will be my built-in electric field. And this will be my external electric field. built-in, external, right? Built-in is more, so this will be the total electric field, and if this is the total electric field, so I can make the slopes very quickly. In this case, you tell me what will be the total electric field? 0, because built-in and external cancelling out each other, so total slope will be 0. And here external is more, since external is more, so total slope will be in this direction. This job is done, job done. Okay, so this job is done. So I'm just telling that quickly I can how I can make it in the examination without thinking too much. Now next I know that this will be the direction of current in all the cases, because from the positive terminal of battery the current will flow. So direction of total current will be, forget about diffusion, drift, sir, I know that this will be the direction of total current. This will be the direction of total current. So in the direction of current, my slope will be positive, right? So my slope should be increasing like this, and I know that, just one correction I will do. Slope should be increasing like this. There should be a positive slope, and I know that here there is more doping. At x equals to 0 there is more doping, and at here there is lesser doping. So this is not flat, it looks like flat. What I should do? Okay, you guys just need to understand that this is not flat. Now it doesn't look like flat. Okay, doesn't look like flat. You just need to show that there is some slope. There is some slope. So this is your EFP. It will be near to the valence band. Yes, it is near to the valence band. Second, the current of the direction of current will be like this. The slope will be positive in this manner. Secondly, here there is more doping. Here there is lesser doping. Job done. Next, there you go. Very simple. This is the direction of current. This is the direction of current. Yes, in the direction of current, slope will be positive. Yes, it is positive. More doping, lesser doping, lesser doping. Here, this will be interesting. What will be the direction of the flow? This will be the direction of the flow, right? More doping, lesser doping. And current will also be flowing in this direction. Current will always come out of the battery. So that's it. This is how I can make my EFP and EFP. Very simple, right? Very, very simple. Just see the current direction, just see the total electric field, just see the current direction, your job is done. And current will be always flowing out of the positive terminal of the battery. That is 100% sure. So if you just flow out of the current, then you will get to know. Here also you can just see in all the example, current is flowing out positive slope. Here in this, current is flowing out like this, positive slope. Positive slope here. Just make sure that here there is more doping, here there is lesser doping. Positive slope here, here there is more doping, lesser doping. Positive slope here, more doping, lesser doping. So make the slope making sure that more doping, lesser doping is also satisfied. Last, both are in the same direction. Then this will be your built-in electric field, and this will be your external electric field, and this will be the direction of total current, because from the positive terminal the current will be flowing out, right? But concept was more important, that how this current is flowing, because a lot of students would get that out, that sir, current can flow out of the negative terminal as well. So diffusion is cancelling out or not. So all these analysis I have explained to you, right? Which diffusion is cancelling out, which drift is cancelling out. So everything I have explained. Now just you need to draw the diagram. So this is the total electric field which are being added. Okay, and this is the direction of current. अरे भाई ये बनाना बहुत मुश्किल हो जाएगा यार. We need to show the slope as well, and I need to make sure that it is increasing in this direction as well. So how will I make it? I need to show the slope as well, and also I need to show that it is increasing as well. First I make this and then I make this. There is more slope. So guys, will you be able to make it, or shall I pause the video and make? I will pause the video and make it. Yeah, so this diagram is fine. Basically slopes should be positive only, no? So slope are positive only. In the direction of decreasing x, all the slopes are positive. This is also positive, this is also positive, this is also positive. In the direction of decreasing x, not increasing x, right? Basically in this direction slope should be positive. So positive, positive, positive. But this slope I need to make sure in a manner that this is my EFP. I need to make sure it should be in a manner that it would be near here and further away from here. So a bit it was tougher to think, but you just think that I just need to make sure that here there is more gap. So this is how, and slope should also be there. So this is how I thought. Then this slope should be equal to this, and this should be equal to this. Okay. So all the concept is clear to you, right? This diagram is made in the examination. In the options, diagram would be made. So you will be able to click very easily, right? And if this diagram is made, then you will be able to think that what is actually happening. Here there is more doping, then total electric field is like this, then you will be able to understand what all things are happening. Okay then. So yeah, this is the end of this lecture. So in this lecture we studied about Fermi Dirac distribution, then we draw the energy band diagram. It was a very fruitful session, because from this particular session the question is surely coming. If they are framing good question on EDC, then from here the problem will surely come. Now almost the syllabus is completed. We need to see some practice problem and one or two concepts we need to see, like what is quasi Fermi level, that we need to see. And there was one more query, right, which I asked in the first session. What that was, that in the conduction band there are electrons, in valence band there are electrons, conduction band is completely empty. At room's temperature, how they are getting enough energy to make a transition from valence band to conduction band, right? Room's temperature, the energy is 26 milli electron volt, but the band gap is 1.1 electron volt. So how this 26 milli electron volt is enough to make a transition from conduction band, from valence band to conduction band? So that question I will answer, right? Because now we have studied Fermi Dirac distribution, so I will be able to answer. And along with that, we will understand about quasi Fermi level, and then we will solve some questions. So next lecture will be of roughly around 1 or 2 hour maximum, and after that everything will be completed. All good, all fine. So I hope you enjoyed the lecture, and don't forget to put a like. If you are watching it on YouTube, don't forget to put a like. Okay, and do share it with your friends, that let them know that these kind of things are being discussed there. These kind of all the diagrams are being discussed there. Every single thing, whatever that can be asked in the examination, every single diagram is discussed there. Okay, and more problems we are going to see. So yeah, just share it, and okay then. Thank you very much. Happy learning.